Imagine everything we think we know about the universe is just a fraction of the truth. We assume space is empty, time moves in a straight line, and gravity is just the force pulling us down. But what if space itself can twist and bend in ways we can't even see? What if the missing pieces of the universe, dark matter and dark energy, aren't just invisible substances but the effects of something deeper, something hidden in the very fabric of space-time itself? For decades, scientists have struggled to explain why galaxies move the way they do. The math doesn't add up. If general relativity is correct, there should be way more mass in the universe than what we can observe. Some theorists say this missing mass is dark matter, some say dark energy is causing the universe to expand at an accelerating rate. But what if our whole understanding of gravity is incomplete? That's where space-time torsion comes in. It's an idea that challenges everything we think we know about gravity. Instead of just curving space like Einstein described, the fabric of reality might also be twisting, spinning, and deforming in ways that could explain all the mysteries we've been struggling to solve. If true, this could change everything, not just how we see the universe, but how we understand reality itself. To understand what this means, let's break it down. In Einstein's general relativity, gravity isn't a force like Newton imagined. Instead, massive objects bend space-time, and other objects move along those curves. That's why planets orbit stars and why light bends around black holes. But this theory has gaps. It doesn't fit with quantum mechanics, it doesn't explain the missing mass in the universe, and it can't fully describe what happens inside black holes. Alternative gravity theories propose that something is missing from Einstein's equations, something beyond just the warping of space. One of the biggest modifications involves adding a property called torsion. Torsion means that space-time isn't just curving, it's also twisting at every point. Imagine space-time as a stretchy sheet, like a trampoline. In general relativity, objects sit on this sheet and create dents. But with torsion, the sheet isn't just bending, it's also twisting like a wrung-out towel. This idea comes from a branch of physics called Einstein-Cartan theory, which modifies general relativity by allowing space-time to have not just curvature but also intrinsic rotation. It suggests that fundamental particles, which have spin, could interact with this torsion in a way that modifies gravity at very small scales. And if that's true, it could mean dark matter and dark energy aren't mysterious, unseen substances but effects of space-time behaving in ways we haven't accounted for. So how would this actually work? If space-time has torsion, then the way matter moves through the universe would be different than we expect. Some models suggest that torsion could mimic the effects of dark matter by subtly changing how galaxies rotate. Instead of needing extra invisible mass, the twisting of space-time itself could be affecting how gravity behaves on cosmic scales. This could explain why galaxies don't fly apart despite their high rotation speeds. And what about dark energy? The accelerated expansion of the universe is one of the biggest unsolved mysteries in physics. Standard explanations rely on a mysterious force stretching space apart. But if space-time itself has an underlying twisting structure, it could create effects that look like dark energy without requiring an unknown new form of energy. Some theories suggest that the twisting of space-time could naturally lead to an expansion effect, making the universe accelerate without the need for an extra force. But here's where it gets even crazier. If torsion is real, it could have massive implications for black holes, wormholes, and even time travel. In Einstein's equations, singularities, points of infinite density, appear at the center of black holes. But in theories with torsion, singularities might not exist at all. Instead of collapsing into an infinitely small point, matter might reach a state where torsion prevents complete collapse, forming something completely different inside a black hole. Some physicists believe torsion could even allow for stable wormholes, hypothetical tunnels in space-time that could connect distant parts of the universe. In normal general relativity, wormholes collapse too quickly to be useful. But in some alternative gravity theories with torsion, the twisting effects could stabilize them, making them theoretically traversable. This raises wild possibilities about faster-than-light travel, time loops, and even the ability to escape black holes. The problem? We don't have direct proof that space-time has torsion. General relativity has been tested extensively, and so far, it matches observations. But there are still anomalies. Certain cosmic phenomena don't quite fit standard models, and some physicists believe these could be signs that torsion plays a role. One possible way to detect space-time torsion is through its effects on particle physics. Since torsion interacts with the spin of particles, it could show up in experiments involving neutrinos or the behavior of elementary particles under extreme conditions. Another approach is looking at the cosmic microwave background, the leftover radiation from the Big Bang. Some theories predict that if space-time had torsion in the early universe, it would leave subtle imprints in this radiation that we might be able to detect. Another potential clue is the behavior of black holes. If torsion is real, it could affect how black holes merge, how they emit gravitational waves, and even how they evaporate over time. Advanced gravitational wave detectors might be able to pick up on these differences and provide evidence for or against space-time torsion. So why hasn't this idea taken over mainstream physics? Part of the reason is that general relativity works really well in most cases, and modifying it is a huge challenge. Every new theory has to match all existing observations while also explaining things general relativity can't. But the search continues. With new telescopes, particle accelerators, and gravitational wave detectors coming online, we may soon get data that either rules out or confirms these ideas. If torsion turns out to be real, it would mean the universe is far stranger than we ever imagined. It would mean spacetime isn't just a passive stage where physics happens, but an active participant in shaping reality. It could rewrite our understanding of gravity, solve the mysteries of dark matter and dark energy, and open up new possibilities for technology, space travel, and even our fundamental understanding of existence. And if that's true, then the biggest secret of the universe has been hiding in the very fabric of reality itself, waiting for us to discover it. If space-time torsion plays a role in gravity, it could mean that our understanding of cosmic evolution is incomplete. Right now, the standard model of cosmology relies on dark matter to explain the formation of galaxies and dark energy to explain why the universe is expanding faster over time. But what if the universe's expansion isn't being driven by an unknown force but by an inherent twisting motion in the structure of spacetime itself? One of the biggest issues with general relativity is that it doesn't naturally explain the universe's accelerated expansion. The equations suggest that gravity should slow everything down over time, not speed it up. That's why dark energy was proposed, because something is counteracting gravity on the largest scales. But if spacetime has an intrinsic torsion, it could mean that expansion is a built-in feature of the universe's structure, not an effect of some mysterious energy. Think of it like this: imagine twisting a rubber band. As you twist, tension builds up, and eventually, the rubber band stretches outward. If spacetime has a similar underlying twisting motion, it could naturally drive expansion. Some models suggest that torsion could create a kind of built-in repulsive force at large scales, which would mimic the effects of dark energy without requiring any unknown particles or fields. And this isn't just speculation. There are real mathematical models that suggest torsion could explain why galaxies rotate the way they do, without the need for dark matter. In standard gravity, galaxies should spin in a way that follows Newton's laws. But observations show that stars on the outer edges of galaxies move way too fast, as if there's extra invisible mass holding everything together. The usual explanation is that dark matter is providing this extra gravitational pull. But theories with torsion suggest that spacetime itself could be responsible. Instead of needing an invisible substance to create extra gravity, the twisting nature of spacetime could change how forces work at galactic scales, naturally accounting for the strange motion of stars without requiring any unseen mass. This could solve one of the biggest mysteries in astrophysics: why dark matter has never been directly detected. Decades of experiments have searched for dark matter particles, but nothing has turned up. No direct evidence, no conclusive signals, just unexplained gravitational effects. If spacetime torsion is real, it could mean we've been looking for the wrong thing this whole time. The effects we've attributed to dark matter might not be caused by any substance at all but by the hidden structure of reality itself. And then there's the question of black holes. These objects are already some of the strangest things in the universe, warping space and time to extreme degrees. But if torsion exists, black holes might not behave the way we think they do. In general relativity, when a massive star collapses, it forms a singularity, a point of infinite density where the laws of physics break down. But if space-time has torsion, it could prevent singularities from forming at all. Instead of an infinitely dense point, the core of a black hole might be something else entirely, something that could even connect to other regions of the universe. Some theories suggest that torsion could allow for structures inside black holes that behave more like exotic matter rather than pure singularities. This could mean that black holes aren't actually one-way destinations where everything is lost forever but instead could contain pathways to other parts of space-time, or even other universes. And what about wormholes? In standard physics, wormholes, bridges between distant points in space-time, are incredibly unstable. The moment anything tries to pass through, the wormhole collapses. But in theories with torsion, these structures could be naturally stable. Instead of needing exotic matter to hold them open, the twisting of spacetime itself could provide the necessary support. If true, this wouldn't just be a wild theoretical possibility. It could change the future of space travel. Instead of needing impossible amounts of energy to reach distant stars, space-time itself could provide shortcuts through the universe. This brings us to one of the biggest implications of all. If space-time torsion is real, it could mean that gravity and quantum mechanics are more connected than we thought. Right now, one of the biggest unsolved problems in physics is that general relativity and quantum mechanics don't fit together. They describe reality in completely different ways, and every attempt to unify them has hit a dead end. But torsion provides a possible link between the two. In Einstein-Cartan theory, the intrinsic spin of particles interacts with space-time torsion. That means that at the smallest scales, gravity isn't just a smooth warping of space, it's also a twisting effect that connects to quantum properties. If this connection is real, it could mean that gravity has been quantum all along, we just haven't been looking in the right way. It could mean that instead of needing a completely new theory to explain quantum gravity, we just need to modify what we already have. But how do we prove any of this? If space-time torsion is real, it should leave subtle traces in the universe. One possible test is through gravitational waves. When massive objects like black holes merge, they send ripples through space-time. If torsion plays a role, these waves should have tiny deviations from what general relativity predicts. Another test comes from neutron stars, ultra-dense remnants of collapsed stars. These objects have extreme gravitational and quantum properties, making them perfect laboratories for testing alternative gravity theories. If torsion exists, it could affect how neutron stars behave, how they emit radiation, and even how they interact with surrounding space. Then there's the possibility of finding evidence in the early universe. The cosmic microwave background, the faint afterglow of the Big Bang, contains imprints of the universe's earliest moments. If torsion was present in the early universe, it could have left subtle signatures in this radiation, which we might be able to detect with advanced telescopes. The search for torsion is still in its early stages, but the implications are staggering. If true, it wouldn't just explain dark matter and dark energy, it would redefine our entire understanding of the universe. It would mean that spacetime isn't just a stage where physics happens but an active, dynamic structure with hidden properties we've only just begun to explore. And if torsion is the key to unlocking these mysteries, it could mean that the biggest discoveries in physics aren't in some distant galaxy or particle accelerator. They're hidden in the very fabric of reality itself, waiting for us to uncover them. If torsion is a fundamental part of spacetime, it raises a huge question. Why haven't we noticed it before? After all, general relativity has been tested over and over, and every experiment so far has confirmed Einstein's predictions. But the key issue is that general relativity is incredibly precise in the weak field limit, that is, in situations like our solar system, where gravity is relatively mild. The extreme conditions where torsion would make a difference, like inside black holes or in the first moments after the Big Bang, are places we can't directly observe. That means torsion could be there, hidden in the strongest gravitational environments, without contradicting anything we've measured so far. It's not that Einstein was wrong, it's that his equations might be missing a deeper layer of reality, one that only becomes obvious under extreme conditions. One of the most interesting consequences of torsion is its potential link to spin. In quantum mechanics, particles like electrons have a property called spin, which isn't literally spinning motion but a kind of intrinsic angular momentum. If spacetime has torsion, it might mean that spin isn't just a quantum property. It's something that interacts directly with the fabric of the universe itself. This would be a radical shift in our understanding of physics. Right now, spin and gravity are treated as separate things. Gravity comes from mass, and spin is a quantum effect. But in theories with torsion, the two are directly connected. This could be the missing piece in unifying quantum mechanics with gravity, something that physicists have struggled with for decades. If spin and torsion are linked, it might also help explain another huge mystery: why the universe has structure in the first place. According to standard cosmology, tiny quantum fluctuations in the early universe were stretched out by cosmic inflation, creating the seeds of galaxies. But inflation itself is a theoretical patch. It's something we had to introduce because the universe looks too smooth without it. What if torsion naturally created these fluctuations? If spacetime had an intrinsic twisting motion in the early universe, it could have generated the irregularities needed for galaxies and stars to form without requiring inflation. This would completely change our understanding of cosmic history. And it gets even weirder. Some researchers have suggested that torsion could play a role in the behavior of neutrinos, the nearly massless particles that pass through everything almost undetected. Neutrinos are already mysterious because they oscillate between different types, something that doesn't happen with other particles. If torsion interacts with neutrinos, it could explain why they behave so strangely, and possibly even hint at a deeper connection between gravity and the weak nuclear force. There's also the question of whether torsion could be detected through anomalies in planetary motion. While general relativity predicts the movements of planets with extreme accuracy, there have been tiny discrepancies in the orbits of certain bodies, like the flyby anomalies, small changes in spacecraft velocities that aren't fully understood. If space-time torsion exists, it could be subtly affecting motion in ways that we've dismissed as measurement errors. But the biggest implications of all come from what this means for the nature of reality itself. If torsion is real, then spacetime isn't just a passive backdrop for physics. It's something dynamic, something that has its own inherent motion. Instead of thinking of the universe as a stage where matter and energy play out their interactions, we'd have to start thinking of spacetime itself as an active participant in shaping reality. This could mean that the fundamental building blocks of the universe aren't particles or even waves, but twists and loops in the structure of spacetime. Some researchers have proposed that elementary particles themselves might be tiny knots or twists in spacetime, meaning that mass, charge, and spin could all emerge from deeper geometric properties. If that's true, then our entire understanding of physics could be about to change. Instead of searching for new particles to explain dark matter, dark energy, and the structure of the cosmos, we might need to rethink what matter and energy actually are in the first place. And this might not just be a theoretical idea. If torsion is real, then it could have technological applications beyond anything we've imagined. Just as Einstein's theories led to GPS and quantum mechanics led to computers, understanding torsion could open the door to manipulating gravity in ways we currently think are impossible. Could torsion allow us to create artificial gravity? Could it be harnessed to make space travel easier, or even to create stable wormholes? If space-time itself has hidden structure, could we learn to shape it, to twist it in ways that let us access new forms of propulsion or communication? These aren't just wild ideas. If torsion is real, then we've only begun to scratch the surface of what's possible. And the biggest discoveries in physics might not come from smashing particles together at higher energies, but from understanding the deep, hidden structure of the spacetime we already live in. If torsion is a fundamental aspect of spacetime, then it might be the key to answering one of the greatest mysteries of modern physics: the true nature of dark matter and dark energy. These two invisible components make up about 95% of the universe, yet we have no direct evidence of what they actually are. Dark matter is inferred from the way galaxies rotate, It behaves like an unseen mass that holds galaxies together. Dark energy, on the other hand, is the unknown force driving the accelerated expansion of the universe. Right now, the dominant theories assume that dark matter is some kind of unknown particle, while dark energy is a mysterious property of empty space itself. But what if these effects aren't caused by new particles or exotic forces, but by the geometry of space-time itself? If torsion exists, it could naturally create the same gravitational effects that we currently attribute to dark matter and dark energy, without requiring any new forms of matter or energy. One way this could happen is through the way torsion alters gravity at large scales. In standard general relativity, the curvature of spacetime is what causes gravity. But if spacetime also has intrinsic twisting motion, it could lead to additional forces that mimic the effects of dark matter. Imagine spacetime as a stretched-out fabric. In normal gravity, mass bends the fabric, creating a dip that other objects fall into. But if the fabric is also twisting, it could create additional distortions that affect how matter moves on a cosmic scale. This could explain why galaxies rotate the way they do. According to standard physics, stars at the edges of galaxies should be moving more slowly than the ones near the center. But in reality, they move almost as fast as inner stars, suggesting that there's extra mass holding them together, mass that we call dark matter. If space-time torsion is at play, it could generate the same effect without the need for invisible matter. Some alternative gravity theories suggest that torsion could act like an additional force, counteracting the effects of gravity at large scales. Instead of dark matter being a physical substance, it might be an effect of how torsion modifies gravitational interactions over long distances. This would explain why dark matter is so difficult to detect. It wouldn't be a new particle at all, but a feature of spacetime itself. Dark energy is even more mysterious than dark matter because it's not just affecting the motion of galaxies. It's changing the expansion rate of the entire universe. For a long time, scientists thought the expansion of the universe should be slowing down due to gravity pulling everything together. But instead, it's speeding up. The current explanation is that empty space has an inherent energy that causes this acceleration. But that explanation feels like a placeholder, something we invented just to make the math work. If torsion is real, it might provide a much more natural explanation. Some theories suggest that torsion could introduce a kind of repulsive force at cosmological scales. This could be similar to how electromagnetism has both attraction and repulsion. Gravity, if modified by torsion, might not just pull objects together but also push them apart under certain conditions. This could explain why the universe's expansion started out slowing down after the Big Bang, as expected from normal gravity, but then suddenly began accelerating. If torsion has a delayed effect, it might only become significant at very large scales, explaining why we see the acceleration happening billions of years after the universe began. One possibility is that torsion interacts differently with different forms of energy. In the early universe, when matter and radiation were dominant, torsion's effects might have been negligible. But as the universe expanded and matter thinned out, torsion might have started to exert a repulsive influence, driving the accelerated expansion we now attribute to dark energy. If this is the case, then our entire understanding of the universe's fate could change. Right now, the leading theory suggests that dark energy will continue to push galaxies apart forever, eventually leading to a cold, empty cosmos where everything is too far apart to interact. But if torsion's effects change over time, the universe's expansion might not be a simple runaway process. Instead, it could fluctuate, slow down, or even reverse under certain conditions. This opens up the possibility of a cyclic universe, where expansion and contraction happen in a repeating pattern. Some theories suggest that torsion could even create regions of spacetime that loop back on themselves, leading to structures that act as cosmic memory, preserving information across different cycles of the universe's evolution. If torsion plays a role in cosmic expansion, then it might also be connected to the phenomenon of cosmic voids, huge empty regions of space that make up most of the universe. These voids are vast, spanning hundreds of millions of light years, and they seem to expand faster than regions filled with galaxies. Standard physics struggles to explain why voids grow at a different rate, but torsion could provide a natural explanation. If spacetime's twisting motion has different effects in high-density and low-density regions, it could drive the formation and expansion of cosmic voids. This could mean that the structure of the universe isn't just shaped by gravity and dark matter, but also by the hidden geometry of spacetime itself. Instead of seeing the universe as a battle between attraction and expansion, we might need to think of it as a dynamic system where the twisting nature of spacetime constantly shifts the balance. Torsion could also have implications for black holes. Right now, black holes are thought to be singularities, points where gravity becomes infinite and the known laws of physics break down. But if spacetime has torsion, then black holes might not be true singularities at all. Instead, the extreme curvature of spacetime near a black hole could create a kind of twisting feedback loop, preventing the formation of a true singularity. This would completely change our understanding of black holes. Instead of being inescapable one-way doors, they might have more complex internal structures, possibly even acting as bridges to other regions of spacetime. Some researchers have suggested that torsion could prevent the total collapse of matter inside a black hole, leading to a scenario where black holes don't destroy information but instead store or transform it in ways we don't yet understand. And if black holes behave differently under torsion-based gravity, it could give us a way to test these theories. Some modified gravity models predict that torsion could create subtle effects in the way black holes interact with their surroundings. If we find evidence of these effects, such as deviations in how black holes merge or how they bend light, it could be the first real sign that torsion exists. Another way to test for torsion is through gravitational waves. When two black holes collide, they send ripples through spacetime. So far, all the gravitational waves we've detected match general relativity's predictions. But if torsion exists, it could slightly alter the shape of these waves, adding extra components that aren't predicted by standard physics. Future gravitational wave detectors might be able to pick up these small differences, providing indirect evidence of torsion's existence. If we do find evidence of torsion, then it could open up a whole new field of physics. Right now, most attempts to go beyond general relativity focus on adding new particles or forces. But if torsion is the missing piece, then the real answer might not be in particle physics at all. It might be hidden in the deep geometry of spacetime itself. And if that's true, then the next great revolution in physics won't come from building bigger particle accelerators. It will come from understanding the fundamental twists and turns of the universe at the deepest possible level. Exploring the deeper implications of spacetime torsion could bring about a profound shift in how we perceive the entire universe. The very structure of space itself could be far more complex than what we currently imagine, and torsion might hold the key to unlocking a vast array of cosmic mysteries. At this point, it's important to step back and appreciate how revolutionary such a discovery would be. For centuries, scientists have been working with the assumption that spacetime is a smooth and continuous fabric. It bends and warps in response to mass and energy, but at its core, it is static and uniform. The introduction of torsion would radically alter this conception, suggesting that spacetime is not just curved but also twisted in ways that we have not yet fully understood. This could imply that the forces governing the universe are far more intricate than the simple, elegant equations of general relativity suggest. The discovery of torsion could also shed light on the elusive nature of the cosmos at the smallest scales. Quantum mechanics and general relativity have long been at odds, unable to reconcile the strange world of subatomic particles with the sweeping grandeur of galaxies and stars. Torsion may provide a bridge between these two realms. At the quantum level, spacetime is thought to be incredibly chaotic, with quantum fluctuations creating ripples in the fabric of space itself. If torsion exists, it could be a manifestation of this chaos, an intrinsic property of spacetime that could unify the very large and the very small. But what does this mean for the future of physics? Could torsion lead to new technologies or new ways of understanding the universe? The answers might be closer than we think. If torsion is a fundamental property of spacetime, then it might not just explain dark matter and dark energy. It could also influence other aspects of our physical reality. Perhaps torsion is the key to understanding phenomena that are currently beyond our reach, such as the behavior of black holes, the formation of galaxies, or even the mechanics of cosmic inflation. Another fascinating prospect is the potential connection between torsion and other cosmological phenomena, such as the so-called anomalous behavior observed in certain stars and galaxies. In recent years, astronomers have discovered that certain celestial bodies appear to be behaving in ways that are not fully explained by conventional theories of physics. Some stars, for example, seem to have unusual rotational velocities or exhibit unexpected emissions of energy. Similarly, certain galaxies appear to be more massive than their visible components would suggest. Could torsion provide the explanation for these strange behaviors, by altering the way gravity works on a cosmic scale? As the research into torsion continues, there may also be unforeseen consequences for our understanding of time itself. Space-time torsion could have implications for the flow of time, altering the way we understand its passage across different regions of the universe. Imagine for a moment that time is not a simple, linear progression, but something that can be twisted and distorted by the very fabric of space-time. This could open up fascinating possibilities, such as time dilation occurring on an even larger scale than we have previously considered, or even the potential for time to loop or fold in on itself. If torsion can modify space-time, then it might also modify the flow of time in ways we cannot yet predict. The quest to understand torsion and its role in gravity is in many ways a quest to understand the very nature of the universe. How did the universe begin? What is the true nature of dark matter and dark energy? What is space itself made of, and how does it shape the reality we experience every day? These are questions that have driven humanity's curiosity for centuries. And now, space-time torsion may be offering us a glimpse into answers that we never thought possible. Of course, it's important to remember that we are still in the early stages of exploring torsion's role in gravity. While the theoretical framework behind torsion is compelling, there is much work to be done to confirm its existence and determine how it fits into the broader picture of modern physics. The mathematical models and predictions are still being refined, and new experimental techniques will be required to test these ideas. But the very fact that torsion is being considered as a serious candidate for explaining some of the most pressing mysteries of the universe shows how far our understanding has come. In the coming decades, we may see the development of new technologies and instruments that can probe space-time in ways that were previously unimaginable. With more powerful telescopes, advanced gravitational wave detectors, and quantum sensors, scientists could soon be able to directly observe the effects of torsion on cosmic structures. These observations might reveal subtle distortions in space-time that could lead to a deeper understanding of the forces shaping the universe. Even more exciting is the possibility that space-time torsion could lead to breakthroughs in our understanding of the early universe. The Big Bang, which remains one of the most fascinating and enigmatic events in the history of the cosmos, might hold the key to understanding torsion's role. If torsion is a fundamental property of space-time, it could have played a crucial role in shaping the universe during its infancy, influencing everything from the distribution of matter to the behavior of dark energy. By studying the early universe, we could learn more about the nature of torsion and how it influenced the evolution of space-time. Furthermore, the exploration of torsion might also change our understanding of the structure of space itself. Today, we think of space as being essentially empty, with matter and energy acting upon it. But if torsion is a fundamental aspect of space-time, then space itself might not be the empty void we once thought it to be. Instead, it could be a dynamic, twisting entity, constantly shifting and evolving as it interacts with the matter and energy within it. This realization could open up new areas of research, allowing us to explore the very fabric of reality itself in ways that were once thought to be the realm of science fiction. As we continue to explore the mysteries of space-time, we may find that the answers to the universe's greatest questions are not just hidden in the distant reaches of space, but within the very structure of space itself. Torsion, if confirmed, could offer us a new lens through which to view the universe, a lens that might reveal hidden patterns, new forces, and a deeper connection between all things. And as we begin to unravel the mysteries of torsion, we may find ourselves on the cusp of a new era in physics, one in which the boundaries between space, time, matter, and energy blur into a unified, elegant whole. The journey to understand space-time torsion is just beginning, but it is already reshaping our perception of the universe. Whether it's through shedding light on the mysteries of dark matter and dark energy, offering new insights into the nature of black holes, or providing a bridge between quantum mechanics and general relativity, torsion has the potential to revolutionize our understanding of the cosmos in ways that we are only beginning to grasp. The universe is far more intricate and mysterious than we ever imagined, and space-time torsion could be the key to unlocking its deepest secrets. As we venture deeper into the implications of space-time torsion, it's crucial to consider how this concept might reframe our understanding of the universe, both at the macro and quantum scales. Space-time torsion isn't just an abstract mathematical theory. It could become a pivotal tool in deciphering some of the most perplexing aspects of the cosmos. One of the primary mysteries that might be explained by space-time torsion is the enigmatic behavior of dark matter. We observe the effects of dark matter through its gravitational influence on visible matter, yet we can't detect it directly, leading to speculation about its true nature. Could space-time torsion be the answer? When we think about dark matter, the image that often comes to mind is that of an invisible force acting on galaxies and galaxy clusters. Traditional models of gravity, based on Einstein's general relativity, can explain many of these phenomena, but they fall short when it comes to providing a concrete explanation of dark matter's origins and its precise role in the universe. If space-time torsion influences gravitational interactions in ways that differ from conventional general relativity, it might be able to explain these anomalies. Instead of invoking the existence of unseen particles that interact weakly with matter, torsion might offer an alternative explanation for the observed gravitational effects, one that doesn't require postulating new types of matter. By incorporating torsion into the framework of general relativity, we might be able to account for the gravitational effects typically attributed to dark matter, without requiring the existence of a new, exotic substance. For example, space-time torsion might affect how mass and energy bend and curve space-time. This could lead to additional corrections to the gravitational field equations, altering the way that mass interacts with the fabric of space-time. These modifications might provide the necessary adjustments to explain the unusual motion of galaxies and galaxy clusters, offering a new perspective on dark matter. Similarly, dark energy, the mysterious force that seems to be accelerating the expansion of the universe, could also be influenced by space-time torsion. Dark energy remains one of the most baffling aspects of modern cosmology. Observations indicate that dark energy accounts for around 70% of the total energy content of the universe, yet its nature remains elusive. Some theories suggest that dark energy is a property of space itself, an intrinsic energy that permeates the vacuum of the universe. If torsion is a fundamental property of space-time, it might play a direct role in shaping the dynamics of dark energy. Torsion could interact with the fabric of space-time in such a way that it contributes to the accelerated expansion of the universe. If space-time is not simply a smooth, curved manifold as we traditionally think, but instead a twisting, dynamic structure, it could create fluctuations that lead to the observed effects of dark energy. These fluctuations might create a form of negative pressure within space-time, which could push galaxies apart and drive the expansion of the universe at an ever-increasing rate. In this context, dark energy might not be an external, invisible force but an intrinsic property of space-time, emerging from the fundamental nature of the universe itself. The introduction of space-time torsion might not only help us explain the observed phenomena of dark matter and dark energy but could also provide a deeper understanding of gravity itself. While Einstein's theory of general relativity has been incredibly successful in describing gravitational interactions on large scales, it has its limitations, particularly when applied to the quantum realm. The unification of general relativity with quantum mechanics is one of the holy grails of modern physics. Space-time torsion could potentially be the missing piece that bridges this gap. At the quantum level, space-time is not smooth and continuous but is thought to be discrete and fluctuating. This chaotic, uncertain behavior might be responsible for the strange, probabilistic nature of quantum mechanics. If torsion exists at this level, it could provide a link between the smooth, macroscopic world of relativity and the chaotic, microscopic world of quantum physics. Instead of treating spacetime as a fixed entity, torsion would imply that spacetime is inherently dynamic, capable of twisting and contorting at the smallest scales. This could lead to new insights into the behavior of particles, fields, and forces at the quantum level, helping us to reconcile the apparent contradictions between quantum theory and general relativity. Moreover, the exploration of space-time torsion could have profound implications for the study of black holes. These enigmatic objects, which warp spacetime to such extremes that not even light can escape, have long been a source of fascination for physicists. Yet despite their central role in modern astrophysics, black holes remain shrouded in mystery. The introduction of torsion could alter our understanding of how black holes form, evolve, and behave. Torsion might provide a new perspective on the singularities at the centers of black holes, potentially resolving some of the paradoxes associated with these cosmic objects. One of the most intriguing aspects of black holes is the information paradox, which arises from the fact that information about matter that falls into a black hole seems to be lost forever. This presents a fundamental problem in quantum mechanics, where the principle of information conservation is a cornerstone. Some theories suggest that torsion might play a role in resolving this paradox. If spacetime is twisted and dynamic at the most fundamental level, it could imply that information is not truly lost but is encoded in the structure of spacetime itself. In this view, the information contained within a black hole might be preserved in a way that we don't yet fully understand, and spacetime torsion could be the key to unlocking this mystery. In addition to its implications for gravity and the structure of the universe, spacetime torsion could also impact our understanding of cosmic inflation, the rapid expansion of the universe in the moments following the Big Bang. Inflationary theory has been successful in explaining many of the large-scale structures we observe today, such as the uniformity of the cosmic microwave background and the distribution of galaxies. However, there are still questions about the details of how inflation occurred and what forces were at play during this period of extreme growth. Torsion could provide an additional mechanism for inflation, potentially offering a more complete description of the early universe. If space-time was twisted during the inflationary epoch, it could have contributed to the distribution of matter and energy in ways that were previously overlooked. This might help explain some of the fine-tuning problems in cosmology, such as the precise balance required for the universe to expand at the correct rate. Space-time torsion could also provide insights into the nature of quantum fluctuations that occurred during inflation, helping us to better understand how the initial conditions of the universe led to the formation of galaxies, stars, and the large-scale structure we observe today. The exploration of space-time torsion is not just a theoretical exercise. It has the potential to revolutionize our understanding of the cosmos. As we continue to study this concept, we may discover new connections between the large-scale structure of the universe and the fundamental nature of space itself. Torsion could provide a unified framework that ties together many of the mysteries of the universe, from dark matter and dark energy to black holes and the early universe. In this way, the study of torsion might hold the key to unlocking some of the deepest secrets of space and time, leading us to a more profound understanding of the universe in which we live. As we stand on the threshold of a new era in cosmology, the potential for groundbreaking discoveries is greater than ever. The role of space-time torsion in alternative gravity theories is a key area of exploration that could reshape the way we think about the universe. Whether it leads to a more complete theory of gravity, helps us understand the behavior of dark matter and dark energy, or provides new insights into the nature of black holes and the early universe, the journey to unravel the mysteries of spacetime is just beginning. The answers we seek may be more twisted, dynamic, and elusive than we ever imagined, but the exploration of spacetime torsion promises to take us further than we ever thought possible. As we continue to explore the intricate relationship between space-time torsion and the fabric of our universe, it's essential to consider how this concept might help reshape the way we view the fundamental forces of nature. The introduction of torsion into our understanding of gravity is not just a minor tweak to existing theories. It has the potential to redefine the very nature of how the universe works. In doing so, it could allow us to uncover new connections between space, time, and matter that have long eluded our grasp. One of the most significant aspects of space-time torsion is its potential to alter our understanding of the relationship between energy and matter. According to the standard model of particle physics, matter is simply a manifestation of energy, and the two are interchangeable, as demonstrated by Einstein's famous equation, E equals mc squared. However, when it comes to the role that gravity plays in this exchange, things become more complicated. Gravity is thought to be the force that governs how matter and energy interact on large scales. But the more we probe this relationship, especially at the extremes of the universe, like in black holes and the very early moments after the Big Bang, the less certain we become about how gravity truly operates. Space-time torsion introduces a new dimension to this relationship, one that could potentially modify the way that energy and matter interact with gravity. By incorporating torsion into the equations of gravity, we might uncover new effects that alter how matter behaves in the presence of strong gravitational fields. These effects could range from subtle corrections to the way light bends around massive objects to more dramatic consequences, such as changes in the way particles move through space-time itself. Torsion could also offer new insights into the behavior of antimatter, which remains one of the most puzzling aspects of particle physics. The study of space-time torsion could even lead us to a new understanding of fundamental particles and forces. One of the goals of modern physics is to unify the four fundamental forces of nature: gravity, electromagnetism, the strong nuclear force, and the weak nuclear force, into a single, all-encompassing theory. This elusive theory of everything has remained out of reach for decades, but space-time torsion could be the key that brings us closer to this ultimate goal. By incorporating torsion into our theories of gravity, we might discover new connections between the fundamental forces that we never previously considered. Consider, for example, the role of torsion in the quantum realm. At the smallest scales, the behavior of particles is governed by the strange and counterintuitive laws of quantum mechanics. These laws have been incredibly successful in describing the interactions of particles, but they also present significant challenges when applied to the theory of gravity. Space-time torsion could provide a way to bridge this gap between the quantum and the gravitational. If torsion is a fundamental property of space-time, it could affect the behavior of particles in ways that we have yet to understand. This could lead to a new kind of quantum gravity, one that accounts for the twisting and warping of space-time itself. This quantum gravity framework might be able to explain some of the strange phenomena that have been observed in the quantum world, such as quantum entanglement and the behavior of particles in strong gravitational fields. It could also provide new insights into the nature of space-time itself, helping us to understand why it behaves the way it does on both macroscopic and microscopic scales. By studying space-time torsion in the context of quantum mechanics, we could unlock the secrets of the universe's most fundamental building blocks. But it's not just the quantum world that stands to benefit from this new perspective. On larger scales, the presence of space-time torsion could have profound implications for the structure and evolution of the universe itself. We've already seen how torsion might explain phenomena like dark matter and dark energy, but it could also provide new insights into the formation of galaxies, the distribution of matter in the universe, and even the fate of the cosmos itself. For example, space-time torsion might offer a new way to think about the formation of galaxies. The current understanding of galaxy formation is based on the idea that gravitational forces cause matter to clump together, eventually forming stars, planets, and other celestial bodies. However, this process is far from fully understood, especially when it comes to the role of dark matter. Torsion could modify the gravitational forces at play, leading to new models of galaxy formation that take into account the twisting nature of space-time. Similarly, torsion might help us understand the fate of the universe on the largest scales. In current models, the expansion of the universe is accelerating due to the influence of dark energy. But what will happen when the universe continues to expand? Will the acceleration slow down, leading to a big freeze? Or will it continue indefinitely, potentially leading to a big rip? Space-time torsion could provide a new framework for understanding this cosmic evolution, offering new insights into the ultimate fate of the universe. On a more philosophical level, the concept of space-time torsion challenges our very perception of reality. For centuries, we've viewed spacetime as a smooth, static fabric that curves in response to the presence of mass and energy. But the introduction of torsion suggests that spacetime might not be so simple after all. Instead of a smooth, continuous entity, spacetime could be a dynamic, twisting structure that behaves in fundamentally different ways depending on the conditions in which it exists. This idea forces us to rethink our understanding of the universe, challenging long-held assumptions and opening up new avenues of exploration. As we continue to explore the role of space-time torsion in alternative gravity theories, we must also consider how this idea intersects with other cutting-edge fields of research. One area that stands to benefit greatly from the study of torsion is the search for a unified theory of physics. We've already touched on how torsion could help bridge the gap between quantum mechanics and general relativity, but it could also play a role in other areas of theoretical physics, such as string theory and loop quantum gravity. String theory, which posits that the fundamental building blocks of the universe are not point particles but rather tiny, vibrating strings, could be deeply connected to the concept of space-time torsion. In string theory, space-time itself is viewed as a dynamic, multidimensional entity, and the addition of torsion might provide a way to describe its complex behavior. By incorporating torsion into string theory, we could gain a deeper understanding of the forces that govern the universe, from gravity to electromagnetism and beyond. Similarly, loop quantum gravity, a competing theory to string theory, aims to reconcile quantum mechanics with general relativity by describing spacetime as a network of discrete loops. The introduction of torsion could provide an important modification to this theory, altering the way that spacetime is quantized and providing new insights into the fundamental structure of the universe. If torsion is a real, physical phenomenon, it could be incorporated into both string theory and loop quantum gravity, helping to unify these two approaches into a more comprehensive theory of everything. The concept of space-time torsion is far more than just a theoretical curiosity. It represents a powerful tool that could revolutionize our understanding of the universe. Whether it leads to new explanations for dark matter and dark energy, modifies our understanding of gravity, or provides new insights into the nature of space-time itself, torsion has the potential to reshape the landscape of modern physics. As we continue to explore this fascinating concept, we may find that spacetime is far more complex and dynamic than we ever imagined, leading to new discoveries that challenge our very understanding of reality. As we venture further into the implications of spacetime torsion, it's important to explore the broader philosophical and practical consequences of integrating this concept into our scientific understanding. The more we study how spacetime can twist and bend in response to matter and energy, the more we realize that our current models of the universe may not be sufficient to explain all the phenomena we observe. If torsion plays a fundamental role in shaping the behavior of spacetime, then it's possible that the laws of physics are much more complex and nuanced than we have yet discovered. Take, for example, the accelerating expansion of the universe. Current models attribute this to the influence of dark energy, a mysterious force that seems to counteract the pull of gravity and drive the universe apart. However, despite its prominence in cosmological theory, dark energy remains one of the greatest unsolved mysteries of modern science. If spacetime itself is subject to torsion, this could lead to a new way of explaining the acceleration of the universe's expansion. The twist and curvature introduced by torsion could alter how spacetime interacts with both matter and energy. In essence, it could provide an alternative explanation for the effects currently attributed to dark energy. Instead of invoking an unknown force, torsion might account for the observed acceleration by altering the fundamental geometry of the universe. This would represent a significant shift in our understanding of cosmology, potentially offering new insights into the behavior of the universe on its largest scales. Similarly, space-time torsion could provide a novel explanation for the enigmatic presence of dark matter. Much like dark energy, dark matter is a concept that arose from our inability to explain the gravitational effects observed in galaxies and clusters of galaxies using only visible matter. Torsion might be able to account for these phenomena by altering the behavior of gravity on large scales, leading to the kind of effects we currently attribute to dark matter. The presence of torsion could modify how galaxies rotate, how gravity works on the largest scales, and how we interpret the distribution of mass in the universe. While the possibility of torsion accounting for dark matter and dark energy is an exciting prospect, it's important to note that these ideas are still in the early stages of development. There are many challenges to integrating torsion into existing theories of gravity, and it will take time for physicists to fully understand its implications. However, the potential rewards are immense. If torsion turns out to be a fundamental property of spacetime, it could revolutionize our understanding of the universe in ways we have yet to imagine. Moreover, the incorporation of spacetime torsion into gravitational theories could help resolve some of the deep inconsistencies between quantum mechanics and general relativity. These two pillars of modern physics have been remarkably successful in their respective domains, but they are fundamentally incompatible in many respects. General relativity works beautifully when dealing with large-scale phenomena like the motion of planets and the curvature of spacetime around massive objects. Quantum mechanics, on the other hand, excels at describing the behavior of particles on the smallest scales, but it has trouble dealing with gravity. By introducing torsion, we could find a way to harmonize these two theories, creating a unified framework that works across all scales. This might be one of the keys to finally unlocking a theory of quantum gravity, which has long been a holy grail for physicists. Such a breakthrough would represent one of the most significant advancements in the history of science, and it could help us answer some of the deepest questions about the nature of the universe. Beyond the theoretical implications, space-time torsion could also have practical consequences for our understanding of black holes, neutron stars, and other extreme cosmic phenomena. Black holes, in particular, remain one of the most puzzling objects in the universe. While we have a basic understanding of how they form and what happens at their event horizons, the inner workings of black holes are still shrouded in mystery. Space-time torsion could play a critical role in explaining the behavior of matter inside black holes. According to general relativity, the core of a black hole is a singularity, an infinitely dense point where spacetime curves to an extreme degree. However, this singularity presents a major problem for physicists, as it represents a point where the laws of physics break down. If torsion is involved, it could modify the geometry of spacetime within a black hole, potentially providing a way to avoid the singularity and offering a more complete description of the black hole's inner workings. Similarly, the study of neutron stars, dense, collapsed remnants of massive stars, could benefit from an understanding of torsion. These stars exhibit extreme gravitational forces that are difficult to describe with our current models of physics. By incorporating torsion into the equations of state that describe the behavior of matter under such extreme conditions, we might be able to develop a more accurate picture of the internal structure of neutron stars and other exotic objects in the universe. Another area where space-time torsion could have profound effects is in the realm of cosmology, particularly in our understanding of the early universe. The first moments after the Big Bang were a time of extreme temperatures, densities, and curvatures of space-time. These conditions are difficult to replicate in modern laboratories, which makes it challenging to test our theories of the early universe. However, if torsion played a significant role in the evolution of spacetime during this period, it could provide new insights into how the universe began and how it evolved to its current state. For example, torsion could modify our understanding of cosmic inflation, the rapid expansion of the universe that occurred just after the Big Bang. Inflationary models rely on the idea that the universe underwent a period of exponential growth, driven by a form of energy known as the inflaton field. Torsion could offer a new way to describe this process, perhaps by altering the dynamics of the inflaton field or by introducing new features into the equations that govern inflation. Such modifications could help us resolve some of the remaining puzzles about the early universe, such as why the universe appears so homogeneous and isotropic on large scales. As we explore these possibilities, it's important to acknowledge the challenges that come with incorporating torsion into our current understanding of gravity and spacetime. The mathematics involved is highly complex, and there are many competing theories that attempt to explain the same phenomena. However, the potential rewards of understanding torsion are so great that it is worth the effort to continue investigating its role in the universe. One of the key hurdles is developing a robust experimental framework to test the predictions of torsion theories. Unlike some of the other concepts in theoretical physics, torsion is not something that can be easily observed with current technology. While we can detect the effects of gravity on large scales, such as the motion of planets or the bending of light around massive objects, the subtle effects of torsion are much harder to pinpoint. However, with advances in observational techniques and the development of new technologies, we may soon be able to detect the presence of torsion in spacetime. For instance, gravitational wave detectors like LIGO and Virgo have already provided us with a new way to observe the universe, detecting the ripples in spacetime caused by the collision of massive objects like black holes. These detectors are highly sensitive and could potentially be used to search for the effects of torsion on the structure of spacetime. Additionally, the development of more powerful telescopes and observatories could allow us to study the behavior of galaxies, stars, and black holes with greater precision, revealing subtle effects that could be attributed to spacetime torsion. Spacetime torsion is a concept that could fundamentally change our understanding of the universe. By altering the geometry of spacetime, torsion offers a new way to explain phenomena like dark matter, dark energy, and the behavior of objects in extreme gravitational fields. As we continue to explore this fascinating idea, we may find that it provides the missing piece of the puzzle in our quest to understand the nature of gravity, the cosmos, and the very fabric of space and time itself. Whether it leads to a unified theory of everything or simply offers new insights into the structure of the universe, the study of space-time torsion represents one of the most exciting frontiers in modern physics. As we continue to explore the potential of space-time torsion, it's crucial to recognize how the incorporation of such a concept could have far-reaching consequences for our entire understanding of the universe. When we introduce torsion into the equations that govern spacetime, we may be unlocking a level of complexity that goes far beyond our traditional understanding of the cosmos. It's as if the universe itself is presenting us with an entirely new lens through which we can observe the fundamental interactions of matter, energy, and gravity. The mathematical framework that describes torsion, while challenging, could help explain why certain phenomena, like dark matter and dark energy, are so elusive and difficult to detect. One of the profound implications of this concept is that torsion could potentially be responsible for some of the most puzzling features of the universe that have resisted explanation for decades. As we've discussed earlier, the mystery of dark matter looms large in the field of cosmology. We observe gravitational effects, such as the way galaxies rotate, that suggest there is far more mass in the universe than we can directly observe. Space-time torsion could help explain these effects by altering the gravitational dynamics on large scales. Instead of invoking invisible particles or strange forms of matter, torsion could provide a geometric explanation for these anomalies, eliminating the need for concepts like dark matter. Similarly, the accelerating expansion of the universe, attributed to dark energy, might also find its resolution through torsion. If space-time itself is capable of twisting and warping in ways we have yet to fully comprehend, it could be this very property that causes the universe to expand at an accelerating rate. Torsion could provide a new geometric mechanism that mimics the effects attributed to dark energy, offering an alternative view of cosmic evolution. This would shift our understanding from the unknown to the well-understood, based on the observable properties of spacetime. It's also important to examine how the introduction of torsion into spacetime geometry could provide a bridge between the relatively well-understood classical descriptions of the universe and the quantum world. As we continue to probe the quantum realm with increasing sophistication, we encounter situations where our current understanding of spacetime breaks down, particularly when trying to unify gravity with quantum mechanics. Torsion may hold the key to reconciling these two disparate realms. If torsion plays a role in shaping spacetime at both large and small scales, it could help us develop a theory of quantum gravity, something that has remained an unsolved problem for physicists for over a century. The idea of unifying gravity with quantum mechanics, through a theory such as quantum loop gravity or string theory, has been a tantalizing dream for many physicists. However, progress has been slow, largely because we lack a framework that can effectively describe both the microscopic and macroscopic worlds. Space-time torsion could fill this gap, offering a bridge between the infinite smallness of quantum mechanics and the vastness of general relativity. But why should we believe that torsion holds the answers to these questions? What makes this concept so revolutionary? The reason lies in the fundamental nature of torsion itself. In contrast to the traditional approach to spacetime, where geometry is solely determined by the distribution of mass and energy, torsion suggests that there is a deeper, more intricate layer to the fabric of spacetime, one that cannot be understood in terms of mere curvature alone. The introduction of torsion into spacetime allows for the possibility that spacetime itself is dynamic in ways we have yet to discover. This could open up entirely new dimensions of understanding, as we learn to navigate a universe that operates on principles far beyond our current imagination. Beyond this, we must consider how torsion could be reflected in the observable universe, in ways that are currently beyond our detection abilities. While we have yet to observe torsion directly, its effects could manifest in subtle ways. For instance, the propagation of light through space could be influenced by torsion in ways that we haven't yet noticed. Some researchers have suggested that light might undergo slight distortions when passing through regions of spacetime that exhibit torsion. These distortions might be detectable in the cosmic microwave background or in the study of distant galaxies. Although this may seem like a far-off possibility, the ongoing development of more sensitive instruments and observational techniques could eventually make these subtle effects observable. In the future, experiments could test whether the universe's expansion, the motion of galaxies, and the behavior of black holes are influenced by torsion, potentially revolutionizing our understanding of the cosmos. As we consider all of this, it's important to recognize that the study of spacetime torsion is still in its early stages. While it offers a tantalizing glimpse into the potential future of cosmology, there are many obstacles to overcome. Physicists must develop new mathematical tools to incorporate torsion into the existing framework of general relativity, and they must also design experiments capable of testing its effects. However, the progress we've made so far suggests that the study of torsion could be one of the most important avenues of research in theoretical physics for the coming decades. We've only just begun to scratch the surface of what spacetime torsion might reveal about the universe. As we continue to push the boundaries of our understanding, it's entirely possible that this concept could provide the key to some of the most profound mysteries in science today. Whether it's explaining dark matter, dark energy, or the nature of quantum gravity, torsion could ultimately be the missing piece of the puzzle, leading us to a deeper, more unified understanding of the cosmos and our place within it. To truly grasp the potential of torsion, we must remember that the history of science is full of moments where seemingly esoteric or impossible ideas turned out to be the foundation of entirely new branches of knowledge. Just as Einstein's theory of general relativity revolutionized our understanding of space and time, the discovery of spacetime torsion could be the next great leap in our quest for knowledge. The mysteries of the universe are vast, and the more we learn, the more we realize how much we still have to discover. At the end of the day, the study of spacetime torsion is not just about solving specific problems. It's about exploring the very nature of reality itself. By embracing the unknown and challenging our preconceived notions of the universe, we open the door to a future where our understanding of the cosmos is deeper and more comprehensive than ever before. Spacetime torsion represents the possibility of a new era in physics, where we move beyond the limitations of our current models and begin to glimpse the true complexity of the universe. As we continue our journey into the mysteries of space and time, one thing is certain: the pursuit of knowledge is far from over. The universe is full of surprises, and as we delve deeper into its secrets, we will no doubt encounter new phenomena, new forces, and new ideas that will reshape our understanding of the world around us. Spacetime torsion is just one of the many frontiers waiting to be explored, and its potential to change the course of scientific discovery is immeasurable. Whether or not torsion is ultimately the key to solving some of the greatest mysteries of the universe remains to be seen. But the fact that it has the potential to radically alter our understanding of spacetime and the cosmos makes it a topic worth exploring in depth. As researchers continue to push the boundaries of what we know, it's clear that the quest for knowledge will only grow more exciting in the years to come. And who knows? In the not-so-distant future, we may look back on this moment as the beginning of a new era in our understanding of the universe. As we continue exploring the intricacies of space-time torsion, it's important to recognize that this idea challenges some of our most fundamental assumptions about the way the universe works. Traditional general relativity, which has served as our cornerstone for understanding gravitational phenomena for over a century, describes space-time as a smooth, continuous fabric that curves in response to the presence of mass and energy. In this framework, gravity is simply the manifestation of this curvature. However, torsion presents a more complex alternative. It introduces the concept that space-time is not just curved by mass and energy, but it can also be twisted, creating a more dynamic and nuanced interaction between matter and the very fabric of space itself. The implications of this twist, quite literally, are profound. Imagine space-time not as a static backdrop, but as something more akin to a fabric that can be twisted, pulled, and manipulated in various directions. In this view, the forces that govern the universe are not only determined by the mass and energy we observe but also by the underlying geometry of space-time itself. This could be the key to understanding why certain phenomena appear to defy conventional explanations. Dark matter, for instance, may not be a form of unseen matter exerting gravitational forces from the shadows. Instead, it could be the result of torsional effects in the fabric of space-time, influencing the motion of galaxies and clusters of galaxies in ways that we are only beginning to comprehend. Incorporating torsion into our models could provide a deeper explanation for the unexpected behavior of galaxies, which often appear to rotate too quickly for the amount of visible matter they contain. According to general relativity, the mass of a galaxy is supposed to dictate the speed at which its stars rotate, but observations show that galaxies spin at speeds far greater than expected, suggesting there is much more mass than we can see. If torsion is at play, it could be altering the gravitational dynamics in these galaxies, making them spin faster without the need for an unseen mass, dark matter. Instead, it could be the twisting of space-time itself, bending the way gravity functions in these systems. This would be a significant breakthrough, as it would allow us to understand galactic rotation without invoking the concept of dark matter at all. Moreover, when we think about dark energy, the mysterious force that is driving the accelerated expansion of the universe, torsion could offer a new and entirely different perspective. Instead of positing that a strange, repulsive force is responsible for pushing galaxies apart, torsion might allow us to reconsider the expansion of space-time itself. Rather than a force pushing against the fabric of space, the twisting of space-time could be creating the observed effects. This could open up the possibility that the accelerated expansion is simply a result of the geometry of the universe, not the presence of a mysterious energy that fills the void. Such a shift in perspective would not only redefine our understanding of cosmology but also resolve one of the most pressing mysteries of modern physics. To truly appreciate the significance of these ideas, we must take a step back and consider the broader implications for the future of theoretical physics. For decades, physicists have been seeking a unified theory, a single framework that can explain both the macroscopic world of galaxies, stars, and black holes, and the microscopic world of quantum particles and forces. Currently, these two realms are described by separate theories: general relativity for the large-scale structure of space-time and quantum mechanics for the behavior of particles. One of the biggest challenges in modern physics is reconciling these two frameworks into a single, unified theory. The inclusion of torsion in our understanding of space-time could provide the key to bridging this divide. Torsion might act as a fundamental property of space-time that manifests on both large and small scales, offering a consistent approach to the laws of physics across all levels of reality. If this concept is incorporated into our models of quantum gravity, it could lead to the development of a more complete theory that explains both the large-scale behavior of galaxies and the tiny, quantum interactions that govern subatomic particles. This is a tantalizing prospect, as it would allow us to move closer to a theory of everything that could answer the deepest questions about the universe and the fundamental nature of reality. However, as exciting as these possibilities are, it's important to acknowledge the challenges that lie ahead in testing the theory of space-time torsion. Our current observational tools are limited, and detecting torsion in the fabric of spacetime may prove to be an extraordinarily difficult task. The twisting of spacetime could be an incredibly subtle phenomenon, one that is difficult to distinguish from other sources of gravitational anomalies. But just as our understanding of the universe has evolved over the past century with the advent of new technology and methods, so too will our ability to detect the effects of torsion. With the continued advancement of space telescopes, gravitational wave detectors, and other cutting-edge instruments, we may one day be able to directly observe the effects of torsion on cosmic scales. In the meantime, researchers are working tirelessly to develop theoretical models that predict the consequences of torsion and suggest ways to test its validity. One promising avenue is through the study of black holes, where the effects of space-time geometry are most extreme. Black holes are regions where the curvature of space-time becomes infinite, and the forces involved are so intense that they offer a natural laboratory for testing the limits of general relativity. If torsion plays a role in space-time dynamics, it could influence the behavior of black holes in subtle ways, potentially providing a detectable signature that would allow scientists to test the theory. For instance, the way matter behaves near the event horizon or the radiation emitted by black holes could offer clues about the presence of torsion in spacetime. In addition, cosmologists are investigating how torsion might manifest in the cosmic microwave background (CMB) radiation. The CMB is the faint afterglow of the Big Bang, and it carries with it information about the early universe. Any influence that torsion has on the expansion of the universe or the formation of large-scale structures could leave a subtle imprint on the CMB, providing an indirect way of testing the theory. The discovery of such an imprint would not only confirm the existence of torsion but would also mark a major milestone in our understanding of the universe's evolution. The potential for space-time torsion to revolutionize our understanding of the cosmos cannot be overstated. It could provide a unified explanation for phenomena as diverse as the rotation of galaxies, the expansion of the universe, and the nature of gravity itself. It may offer a way to bridge the gap between general relativity and quantum mechanics, bringing us one step closer to a unified theory of everything. Most importantly, it could fundamentally change our perception of space, time, and the forces that govern them. As we continue to explore the mysteries of the universe, the study of space-time torsion offers a glimpse into a future where our understanding of reality is more complete, more elegant, and more unified than ever before. The road ahead is still long and uncertain, but with each new discovery, we come closer to unlocking the secrets of the cosmos. Torsion is just one of many possibilities on this journey, but it's one that holds the potential to reshape the way we think about the universe and our place within it. The future of physics is full of possibilities, and torsion might just be the key to opening up a new chapter in our quest for knowledge. As we continue to explore these ideas, we move ever closer to answering the questions that have puzzled humanity for centuries. What is the nature of space and time? What is the true structure of the universe? And most intriguingly of all, what are the hidden forces that shape our reality in ways we cannot yet fully understand? In the coming years, as we develop better tools and deeper insights, the mysteries of space-time torsion may begin to unravel. And when they do, we may find ourselves standing on the threshold of a new era in our understanding of the universe, an era that promises to be just as groundbreaking and awe-inspiring as the discoveries that came before it. As the quest to understand space-time torsion unfolds, it's crucial to recognize that this idea isn't just another obscure concept in theoretical physics. It's a profound challenge to the very way we perceive the universe. It may redefine our relationship with gravity, dark matter, dark energy, and the fabric of space-time itself. But why does space-time torsion hold such promise for changing the landscape of modern physics? To answer this, we need to further explore the significance of torsion in the broader framework of alternative gravity theories. At its core, space-time torsion proposes that space and time are not just passive containers for matter and energy, but rather active participants in the interactions that define the universe. In contrast to the traditional view, where space-time curvature, brought about by massive objects like stars, planets, and black holes, determines gravitational effects, torsion suggests that the twisting of space-time itself could play a pivotal role in shaping the universe's dynamics. Torsion adds an additional layer of complexity to our understanding of gravity, one that could, as mentioned earlier, help explain otherwise perplexing phenomena such as dark matter and dark energy. In the context of alternative gravity theories, torsion opens up new possibilities for understanding how matter and energy interact with space-time. For example, one of the key questions in cosmology is why the universe is expanding at an accelerating rate. The prevailing explanation involves dark energy, a mysterious and invisible force that is pushing galaxies apart. However, the nature of dark energy remains elusive, and its exact mechanism is still a topic of debate. What if, instead of being a new force, the accelerated expansion of the universe could be explained by a modification to the geometry of space-time itself? This is where torsion comes in. In theories that incorporate space-time torsion, the expansion of the universe might not require an exotic substance like dark energy. Instead, the twisting of space-time could naturally lead to the observed accelerated expansion. This idea challenges the traditional model of cosmology, which relies heavily on dark energy, and offers an intriguing alternative explanation. By adjusting the geometry of space-time through torsion, it may be possible to account for the acceleration of cosmic expansion without invoking an unknown force. Beyond dark energy, torsion could also provide a novel explanation for the mysterious phenomenon of dark matter. As mentioned earlier, the behavior of galaxies and galaxy clusters suggests the presence of unseen mass exerting gravitational influence. But what if this unseen mass wasn't matter at all, but rather the result of twisted spacetime that alters the way gravity behaves on large scales? Instead of requiring a new, invisible substance like dark matter, torsion could explain the anomalous gravitational effects we observe in galaxies. By modifying the laws of gravity through spacetime torsion, it may be possible to replicate the effects attributed to dark matter without requiring the existence of this mysterious substance. These ideas are not just theoretical musings. They are actively being explored in various branches of modern physics. Researchers are working to refine mathematical models that incorporate torsion into gravity theories and cosmological models. One promising approach is the so-called Einstein-Cartan theory, which extends general relativity to include torsion. This theory suggests that torsion can be incorporated into the equations that describe the curvature of spacetime, providing a more complete description of gravitational interactions. According to this framework, the presence of torsion could influence the motion of matter, the propagation of light, and even the expansion of the universe itself. The Einstein-Cartan theory and other similar models offer a fertile ground for exploring the role of torsion in explaining dark matter, dark energy, and other cosmic phenomena. Another area where torsion could play a pivotal role is in the study of black holes. As we delve deeper into the behavior of these enigmatic objects, we begin to realize that our current understanding may not be complete. Black holes are regions of spacetime where the gravitational pull is so intense that not even light can escape. Their mysterious nature presents a challenge to physicists, as they represent a boundary where the laws of general relativity and quantum mechanics appear to break down. The inclusion of torsion in our models of black holes could provide new insights into the behavior of matter and energy at these extreme scales. For instance, recent research suggests that torsion might have a significant impact on the thermodynamics of black holes. One of the central puzzles in black hole physics is the so-called information paradox, which questions what happens to the information that falls into a black hole. According to traditional theory, this information is lost forever, which contradicts the principles of quantum mechanics. However, the introduction of torsion into black hole physics could offer a resolution to this paradox. By modifying the spacetime geometry around black holes, torsion may allow for the preservation of information in ways that we are just beginning to understand. Furthermore, torsion could influence the formation and evolution of black holes in unexpected ways. If spacetime is not simply curved but also twisted, it might alter the way black holes form, grow, and interact with their surroundings. This could lead to new types of black holes that behave differently from those described by general relativity, offering exciting opportunities for further exploration. For example, torsion might enable the creation of exotic black hole configurations, such as rotating black holes with unique properties, or even entirely new types of cosmic objects that lie beyond our current understanding. As we continue to investigate space-time torsion and its potential role in alternative gravity theories, it's clear that we are entering an era of profound discovery. The implications of these ideas extend far beyond the realms of dark matter and dark energy. They touch on the very foundations of our understanding of the universe. If torsion proves to be a key ingredient in the fundamental nature of space-time, it could lead to a radical revision of our current theories and open up new avenues of exploration in both theoretical and observational physics. However, it's important to remember that we are still in the early stages of this journey. While the theoretical foundations of space-time torsion are becoming clearer, much work remains to be done before we can fully understand its implications. Testing these ideas in the real world will require advanced technology, novel experimental approaches, and a willingness to question some of our most deeply held beliefs about the universe. But as history has shown, it is precisely through such bold and innovative thinking that the most significant breakthroughs are often made. The exploration of space-time torsion represents a fascinating frontier in the search for a deeper understanding of the cosmos. Whether it leads to new insights into dark matter, dark energy, black holes, or the very structure of space-time itself, it has the potential to reshape our view of the universe in ways that we can scarcely imagine. As we continue to unravel the mysteries of space and time, torsion could be the missing piece of the puzzle that brings us closer to unlocking the fundamental secrets of the universe. And so, the journey into the unknown continues. The study of space-time torsion is not just about uncovering a new theoretical framework. It is about rethinking the very nature of reality itself. By daring to challenge the conventional wisdom and embrace new ideas, we are paving the way for a future where our understanding of the universe is more profound and more complete than ever before. As we push the boundaries of knowledge, one thing is certain: the universe holds many more secrets, and space-time torsion may just be the key to unlocking them. As we venture deeper into the theoretical and experimental realms of space-time torsion, it becomes increasingly clear that the implications of these ideas reach far beyond the confines of physics. They could profoundly impact our understanding of fundamental concepts such as causality, time, and the very nature of reality itself. To fully appreciate the magnitude of these implications, it's important to look at how these theories could lead to new insights about the most enigmatic and elusive aspects of the universe. Consider, for example, the idea of time itself. In traditional general relativity, time is treated as a dimension within the space-time continuum that is inextricably linked to the three spatial dimensions. However, the introduction of torsion adds a new layer to this framework, potentially altering our understanding of how time behaves in different regions of space-time. By twisting the fabric of space-time, torsion could influence the passage of time itself. In areas where space-time is highly twisted, such as near black holes or in the early universe, time might behave in ways that are fundamentally different from our everyday experience. This could have profound implications for the concept of time travel, causality, and the relationship between past, present, and future. Moreover, torsion could also play a significant role in the study of quantum gravity, a field that seeks to reconcile general relativity with quantum mechanics. Quantum gravity aims to unify the two pillars of modern physics: the theory of relativity, which describes the large-scale structure of the universe, and quantum mechanics, which governs the behavior of particles on the smallest scales. Currently, these two theories are incompatible in certain extreme conditions, such as within the singularity of a black hole or during the early moments of the Big Bang. By incorporating space-time torsion into quantum gravity, researchers hope to create a more unified framework that can explain phenomena at both macroscopic and microscopic levels. This could lead to a deeper understanding of the quantum nature of space-time and provide new insights into the behavior of fundamental particles. One of the most exciting aspects of space-time torsion is its potential to unlock new dimensions of the universe. Dimensions that are not simply theoretical constructs, but may exist in reality, hidden from our perception. If torsion truly influences the shape and structure of space-time, it could suggest the existence of higher dimensional spaces, or even parallel universes. These higher dimensions might not be directly observable with our current technology, but could have subtle effects on the physical laws that govern our universe. By exploring torsion and alternative gravity theories, we may eventually uncover evidence for these hidden dimensions, opening up entirely new realms of discovery. In addition to the potential for new dimensions, the study of space-time torsion could also lead to a rethinking of the very nature of gravity. Traditionally, gravity is seen as the force that governs the motion of massive objects, bending the fabric of space-time as described by general relativity. However, if torsion plays a significant role in shaping the gravitational field, it could lead to a more nuanced understanding of how gravity operates on both large and small scales. For example, the introduction of torsion could affect the behavior of gravitational waves, the ripples in space-time caused by accelerating masses. Torsion could modify the way these waves propagate, leading to new predictions that could be tested through future gravitational wave observatories. As we continue to probe the mysteries of space-time torsion, we must also consider the broader implications of these theories for our understanding of the universe's origin and ultimate fate. One of the most profound questions in cosmology is the nature of the Big Bang, the event that gave rise to the universe. While general relativity and the standard model of cosmology provide a framework for understanding the early universe, there are still many unanswered questions, particularly about the first moments after the Big Bang. If torsion is indeed a key factor in the structure of space-time, it could offer new insights into the very beginning of the cosmos. Perhaps torsion played a role in the creation of the universe itself, influencing the distribution of matter and energy during the earliest moments of cosmic evolution. Furthermore, the concept of torsion may offer new ways to understand the ultimate fate of the universe. While the current standard model predicts an ever-expanding universe, the eventual fate of this expansion remains uncertain. Will the universe continue to expand indefinitely, eventually reaching a state of heat death? Or will it collapse in on itself in a big crunch? The inclusion of torsion in alternative gravity theories could offer a new perspective on these questions. For example, if torsion affects the expansion of the universe, it could provide an explanation for the current acceleration of cosmic expansion and predict a new outcome for the ultimate fate of the cosmos. Instead of the heat death or the big crunch, torsion might suggest an entirely different scenario, one in which the universe undergoes a dramatic transformation that is beyond our current understanding. As we move forward in this line of inquiry, it is important to acknowledge the challenges and uncertainties that lie ahead. The study of space-time torsion is still in its infancy, and many of the ideas discussed here are speculative. However, the potential rewards of further exploration are immense. By pushing the boundaries of our knowledge and embracing alternative gravity theories, we are opening up new avenues of inquiry that could lead to groundbreaking discoveries about the nature of the universe. It is also worth noting that the study of torsion and alternative gravity theories could have far-reaching implications beyond the realm of cosmology and theoretical physics. These ideas could influence other fields of science, such as particle physics, astrophysics, and even the philosophy of science. By challenging the assumptions that underlie our current understanding of gravity and space-time, torsion could lead to a paradigm shift that transforms the way we think about the universe and our place within it. The exploration of space-time torsion represents one of the most exciting frontiers in modern physics. By considering torsion as a key element of alternative gravity theories, we are opening up new possibilities for understanding dark matter, dark energy, black holes, and the very structure of space-time itself. While much work remains to be done, the potential implications of these ideas are profound. If torsion proves to be an essential component of the universe's underlying fabric, it could rewrite the laws of physics as we know them and unlock new dimensions of reality. As we continue to push the boundaries of knowledge, one thing is certain: the mysteries of space and time are far from being fully unraveled, and the discovery of space-time torsion could be the key to unlocking the next great chapter in the story of the cosmos. As we push forward into the unknown, we must consider the tools and approaches that could aid us in verifying the role of space-time torsion in shaping our universe. The first challenge lies in the fact that space-time torsion, by its very nature, is incredibly subtle and difficult to detect directly. Traditional methods of observing space-time are limited by the tools and technologies we currently possess. Nevertheless, advancements in observational techniques, including those related to gravitational wave detection, quantum measurements, and astrophysical observations, may one day provide the key to confirming the existence of torsion and its impact on the cosmos. One potential avenue for testing space-time torsion is through the study of gravitational waves. These ripples in space-time, first predicted by Einstein in 1915 and confirmed through observations in recent years, carry information about the events that produced them. Researchers are particularly interested in the possibility that torsion could alter the way gravitational waves propagate through space. If torsion exists and influences gravitational waves, we could observe subtle variations in the way these waves behave, especially when they pass through regions of spacetime where torsion is most pronounced, such as near black holes or other extremely dense objects. Gravitational wave observatories, such as LIGO, Laser Interferometer Gravitational Wave Observatory, and Virgo, are already making groundbreaking discoveries, detecting the collision of black holes and neutron stars. As these observatories improve and become more sensitive, they may be able to detect the minute effects of torsion on the propagation of gravitational waves. Such observations could provide vital evidence supporting the existence of torsion and, in turn, offer deeper insights into the nature of gravity itself. Another important aspect of testing space-time torsion lies in the study of black holes. These incredibly dense objects warp space-time to an extreme degree, and they represent one of the most promising environments in which to search for signs of torsion. In the presence of strong gravitational fields, such as those around black holes or neutron stars, the effects of torsion could become more pronounced. The powerful gravitational forces near these objects may enhance the twisting of space-time, potentially making torsion detectable through the behavior of light or the dynamics of matter in their vicinity. The recently launched Event Horizon Telescope, EHT, which captured the first image of a black hole in 2019, is one of the most advanced tools for studying these objects. As future advancements in imaging and observational techniques enable us to probe even deeper into the mysterious hearts of black holes, we may gain the ability to observe the effects of space-time torsion directly. This could be done by monitoring the motion of material in the accretion disk, the orbits of nearby stars, or the behavior of gravitational waves emanating from these regions. In addition to gravitational wave observations and black hole studies, space-time torsion could also leave its mark in the cosmic microwave background, CMB, the faint radiation left over from the Big Bang. The CMB is a critical piece of evidence in our understanding of the early universe, as it provides a snapshot of the universe's state just a few 100,000 years after the Big Bang. If torsion had a significant effect on the evolution of the early universe, it might manifest in subtle irregularities or distortions in the CMB. By studying the CMB in greater detail, scientists could uncover clues that support or refute the idea of torsion and its role in the formation of cosmic structures. Moreover, space-time torsion could have implications for the behavior of particles at both the macroscopic and microscopic scales. The concept of torsion is deeply tied to the fabric of spacetime, so its effects might be observable in the behavior of matter itself. For instance, experiments involving precision measurements of the motion of test particles, particularly in regions with intense gravitational fields, could reveal deviations from predictions based on general relativity alone. These measurements could provide indirect evidence of torsion, as even minute effects on the motion of particles could accumulate over time, allowing researchers to detect patterns that are inconsistent with the standard model of gravity. The search for dark matter and dark energy, two of the most profound mysteries in modern physics, is another area where space-time torsion may offer an explanation. Dark matter, which is thought to make up roughly 27% of the universe's mass-energy content, interacts gravitationally with ordinary matter but does not emit, absorb, or reflect light, making it invisible to traditional observational techniques. Dark energy, which is believed to account for around 68% of the universe's energy density, is responsible for the accelerated expansion of the cosmos. Both dark matter and dark energy are elusive and poorly understood, but they could be linked to the concept of space-time torsion. The introduction of torsion into alternative gravity theories could alter our understanding of gravity on cosmological scales, potentially explaining the effects attributed to dark matter and dark energy. For example, torsion could modify the way that gravity interacts with matter, leading to the observed anomalies in galactic rotation curves that have been interpreted as evidence for dark matter. Similarly, torsion could provide a mechanism for the accelerated expansion of the universe, offering an alternative to the current explanation that involves dark energy. The possibility that torsion could explain dark matter and dark energy is a tantalizing prospect. If it is true, it would mean that these mysterious components of the universe are not composed of exotic particles or unknown fields, but rather are the result of the fundamental structure of spacetime itself. In this scenario, spacetime torsion would represent a fundamental aspect of the universe's fabric, influencing the behavior of matter and energy on a grand scale. As we explore these ideas, we must also recognize that the study of spacetime torsion is not just about uncovering new physical phenomena. It is also about challenging our fundamental assumptions about the nature of the universe. The introduction of torsion into our understanding of gravity and spacetime forces us to rethink long-standing concepts such as the smooth and continuous nature of spacetime. It forces us to reconsider the idea that spacetime is a static and unchanging backdrop against which events unfold. Instead, torsion suggests that spacetime itself is dynamic, subject to twisting and contorting in ways that we have yet to fully comprehend. This new perspective on spacetime opens up a wealth of possibilities for future research. The study of torsion could lead to the discovery of entirely new physical laws, new particles, and new forces that have remained hidden from our view. It could redefine our understanding of the universe's evolution, from the Big Bang to the present day, and offer fresh insights into the ultimate fate of the cosmos. Ultimately, the exploration of spacetime torsion is a journey into the heart of the universe itself. It is a journey that promises to reveal the deepest secrets of existence, unlocking new dimensions of reality, and challenging our perceptions of space, time, and gravity. As we continue to push the boundaries of our understanding, we are not only uncovering the hidden mechanics of the cosmos, but also rewriting the very story of the universe, one twist of spacetime at a time. As we venture deeper into the mysteries of spacetime torsion and its potential implications, it's important to acknowledge that we are exploring a realm of theoretical physics where conventional wisdom may no longer hold true. In the same way that general relativity and quantum mechanics have transformed our understanding of the cosmos, the idea of spacetime torsion could usher in a new era of discovery. But this journey, while fascinating, is also full of uncertainty. The mathematical formulations behind torsion are intricate, and the experimental evidence remains elusive. However, that doesn't mean that progress isn't being made. The concept of torsion arises from a deeper, more fundamental theory of gravity, one that extends beyond the confines of general relativity. While Einstein's theory of general relativity offers an elegant description of gravity as the curvature of spacetime, it does so under the assumption that spacetime is smooth and continuous. Torsion, on the other hand, suggests that spacetime is not only curved but also twisted, introducing additional degrees of freedom to the fabric of the cosmos. This twist could have profound implications for how we understand everything from the nature of gravity itself to the behavior of dark matter, dark energy, and beyond. As we previously discussed, torsion could be responsible for the mysterious phenomena we associate with dark matter. For decades, scientists have observed that galaxies spin faster than expected based on the visible matter they contain, suggesting the presence of some unseen, mysterious substance that is exerting a gravitational influence. Conventional theories propose that this unseen mass is made of particles that don't interact with light, but their nature remains a mystery. Torsion offers an alternative explanation. Instead of positing the existence of invisible particles, torsion could alter the way gravity works, making it appear as though there is more matter than we can see. In the same way, torsion could also offer an explanation for dark energy. The accelerated expansion of the universe has puzzled scientists for years. The current understanding suggests that a mysterious energy field, known as dark energy, is causing the acceleration. However, if spacetime itself is subject to torsion, the observed effects of accelerated expansion could be a natural consequence of the twisting of spacetime. This would eliminate the need for exotic forms of energy and matter, and instead, offer a more natural and unified approach to understanding the forces that shape the universe. Another exciting prospect lies in the connection between torsion and quantum mechanics. Quantum gravity is one of the most elusive fields of theoretical physics, aiming to combine the principles of general relativity with quantum mechanics into a single cohesive theory. One of the primary challenges in this pursuit is reconciling the fact that quantum mechanics operates on the very small scales of particles, while general relativity governs the large-scale structure of the universe. Torsion could play a key role in bridging these two realms. By modifying the structure of space-time at the quantum level, torsion may offer new insights into the nature of quantum fields, particle interactions, and the behavior of matter and energy on the smallest scales. In this sense, the study of space-time torsion could help us uncover a deeper connection between the forces that govern the microscopic world of quantum mechanics and the macroscopic world of gravity. This could potentially lead to the long-awaited unification of the fundamental forces of nature, answering one of the most profound questions in physics. Such a breakthrough would not only change our understanding of gravity, but also reshape our ideas about the very fabric of reality itself. While torsion theory remains largely speculative, it is not without its champions. A number of researchers are actively working to refine the mathematical models that incorporate torsion into the framework of general relativity. These models involve complex tensor calculus and spinous, mathematical tools that allow us to describe the twisting of spacetime in precise terms. These efforts are still in their early stages, but the potential to uncover new physics is too great to ignore. In addition to theoretical developments, there is a growing interest in experimental physics, where researchers are developing new ways to detect the effects of torsion. One promising approach involves the use of ultrasensitive gyroscopes and interferometers. These instruments can measure minute changes in the orientation of objects, and some scientists believe they could be sensitive enough to detect the twisting of spacetime itself. If torsion does indeed affect the geometry of spacetime, these instruments may offer the first direct evidence of this phenomenon. Another promising avenue of research is the study of cosmological phenomena at the largest scales. The structure of the universe, including the distribution of galaxies and clusters of galaxies, could provide valuable clues about the nature of spacetime. If torsion influences the way gravity operates on these scales, we might see subtle variations in the behavior of large-scale cosmic structures. By analyzing the cosmic web, the vast network of galaxies and dark matter, we may be able to detect the influence of torsion and refine our models of the universe's evolution. One of the most exciting prospects in this realm is the study of the early universe, specifically the first moments after the Big Bang. During this period, the universe was incredibly hot and dense, and the forces that shaped it were in a state of extreme flux. Torsion could have played a significant role in the formation of the early universe, influencing everything from the distribution of matter to the behavior of the fundamental forces. By studying the cosmic microwave background (CMB), the faint remnants of the Big Bang, we may be able to uncover evidence of torsion's role in the early universe. Any irregularities or patterns in the CMB that deviate from current models of cosmology could be indicative of torsion's influence during the universe's infancy. As we continue to explore the mysteries of space-time and dark matter, the role of torsion may become clearer. It could revolutionize our understanding of gravity, offering a new perspective on some of the most perplexing questions in physics. With the potential to explain dark matter, dark energy, and the nature of gravity itself, the theory of spacetime torsion represents one of the most exciting frontiers in modern physics. The path ahead is filled with challenges, but the rewards could be nothing short of transformative, changing the way we view the cosmos and our place within it. As we continue to delve into the complex and fascinating concept of spacetime torsion, the prospect of uncovering a unified framework for understanding the universe becomes ever more tantalizing. The intricate connections between dark matter, dark energy, and torsion represent just the beginning of the potential discoveries that lie ahead. If torsion indeed plays a role in shaping spacetime itself, it could open the door to entirely new ways of thinking about the forces that govern the cosmos. In traditional general relativity, gravity is understood as the curvature of spacetime caused by the presence of mass and energy. However, torsion challenges this view by introducing a new dimension to the fabric of space-time. Instead of simply curving under the influence of mass, space-time might also twist, with the curvature and torsion working together to influence the behavior of objects and particles. This added complexity could be key to resolving some of the deepest mysteries in physics, including the nature of dark matter and dark energy. Consider, for example, the behavior of galaxies. For decades, astronomers have observed that galaxies rotate at much higher speeds than what would be expected based on the visible matter they contain. This discrepancy suggests the presence of an unseen form of matter, known as dark matter, which exerts a gravitational pull on the visible matter. The problem, however, is that dark matter has yet to be directly detected, and its properties remain largely unknown. One of the ideas that has emerged in response to this mystery is that the effects we attribute to dark matter might instead be due to a modification of gravity itself. If space-time is not only curved but also twisted by torsion, it could cause gravitational effects that mimic the presence of additional mass. This would explain why galaxies appear to rotate faster than expected, without needing to invoke the existence of dark matter particles. Similarly, torsion could offer a novel explanation for the accelerating expansion of the universe, a phenomenon that has long been attributed to dark energy. The discovery that the universe is expanding at an increasing rate was one of the most surprising findings of modern cosmology. While dark energy is the leading candidate for explaining this acceleration, its exact nature remains a mystery. If space-time is subject to torsion, the twisting of the fabric of space-time itself could cause the observed acceleration. This would suggest that the expansion of the universe is not driven by some mysterious energy field, but by the inherent properties of space-time itself. Such a realization would have profound implications for our understanding of the universe's fate, possibly altering predictions about its ultimate expansion or contraction. However, while the theoretical potential of space-time torsion is vast, there are still significant challenges that must be overcome before we can fully embrace its role in explaining these cosmic phenomena. One of the key hurdles is the lack of experimental evidence for torsion. Despite the mathematical elegance of torsion-based models, they remain speculative, and no direct observations have yet confirmed the existence of torsion in space-time. For scientists to move forward with this theory, they need concrete evidence that can support or refute the predictions made by torsion models. Current experimental efforts are primarily focused on detecting torsion's effects at the quantum level. As mentioned earlier, ultrasensitive gyroscopes and interferometers are among the most promising tools for detecting minute changes in the curvature or twisting of space-time. These instruments are capable of measuring extremely small variations in the direction of rotation, which could reveal the influence of torsion. The challenge here lies in the precision required to detect such small effects. The twisting of space-time, if it exists, is likely to be incredibly subtle, and detecting its influence may require instruments far more sensitive than what we currently possess. Beyond laboratory experiments, there is also the potential for astronomical observations to provide indirect evidence of torsion's role in the universe. As we've seen, torsion could influence the rotation of galaxies, the behavior of cosmic structures, and even the expansion of the universe itself. By carefully analyzing the distribution of galaxies, the cosmic microwave background, and other large-scale structures, astronomers may be able to identify patterns that suggest the presence of torsion. If torsion does indeed play a significant role in shaping the universe, it could leave behind subtle signatures in the way galaxies move and the way the universe has evolved over time. Additionally, studying the behavior of fundamental particles could provide insight into the role of torsion at the quantum level. Theories of quantum gravity, which attempt to reconcile general relativity with quantum mechanics, often incorporate torsion as a key component. If torsion is a fundamental aspect of spacetime, it could have profound implications for the behavior of particles in high-energy environments, such as those found near black holes or during the early moments of the Big Bang. Understanding how torsion affects the quantum world could help us uncover new physical laws and open up entirely new areas of research in both cosmology and particle physics. Despite the challenges, there is reason to be optimistic about the future of space-time torsion research. As our technology improves and our understanding of the universe deepens, We may soon find the evidence that confirms or disproves the role of torsion in shaping the cosmos. Whether or not torsion turns out to be the key to understanding dark matter and dark energy, it is clear that it holds the potential to revolutionize our understanding of the universe. The twisting of spacetime, a concept once thought to be purely theoretical, could hold the answers to some of the most profound questions in physics. The study of spacetime torsion offers an exciting and promising avenue of research for physicists, cosmologists, and astronomers alike. As we continue to explore the nature of gravity, dark matter, dark energy, and the fundamental structure of the universe, the possibility that spacetime itself is twisted, rather than merely curved, may provide the key to unlocking some of the most persistent mysteries in science. Whether torsion is the solution to the dark matter and dark energy conundrum or a stepping stone toward a more unified theory of gravity, one thing is certain: the exploration of this mysterious concept is far from over. It may take years, or even decades, of research to fully understand the implications of torsion, but the journey promises to be one of the most thrilling and transformative in the history of physics. As we move forward in our exploration of space-time torsion and its implications for our understanding of gravity, dark matter, and dark energy, it's essential to consider the broader philosophical and scientific shifts that such a theory could introduce. Space-time torsion might not only reshape our view of the cosmos but also challenge some of the most fundamental assumptions underlying the way we think about the universe and the laws that govern it. For centuries, physics has been largely dominated by the idea that gravity is the force that governs the large-scale structure of the universe, from the behavior of planets to the motion of galaxies. Albert Einstein's theory of general relativity, which describes gravity as the curvature of spacetime in the presence of mass and energy, has stood as the bedrock of modern physics. However, as we've seen, this theory leaves several important questions unanswered. It doesn't fully explain dark matter or dark energy, and it's not easily reconciled with the laws of quantum mechanics, which govern the behavior of particles at the smallest scales. Space-time torsion offers a potential modification to general relativity that could provide new insights into these mysteries and help bridge the gap between the macroscopic and quantum worlds. To truly appreciate the potential of space-time torsion, it's important to understand its roots in the broader context of modified gravity theories. Over the years, physicists have proposed several alternatives to general relativity in an effort to explain phenomena that can't be fully accounted for by Einstein's equations. Some of these theories incorporate modifications to the geometry of spacetime, while others introduce new fields or forces that act alongside gravity. Spacetime torsion is just one such modification, but it's one that has garnered increasing attention because of its ability to address some of the most pressing questions in cosmology. One of the most striking features of torsion-based models is their ability to naturally incorporate spin. In classical general relativity, spacetime is treated as a smooth, continuous manifold, without any intrinsic properties like spin. However, quantum mechanics tells us that particles, especially fermions, possess a property known as spin, which can affect their behavior in profound ways. The inclusion of torsion allows for a connection between the geometry of spacetime and the spin of particles, leading to the possibility that spacetime itself is not only curved but also twisted at a fundamental level. This twist could have far-reaching consequences, potentially explaining phenomena that traditional gravity theories cannot. One of the implications of incorporating torsion into our understanding of gravity is the potential to unify different forces of nature. For much of modern physics, the quest for a theory of everything, a unified theory that can explain all of the fundamental forces, from gravity to electromagnetism and the strong and weak nuclear forces, has been one of the holy grails of scientific research. While progress has been made, the goal remains elusive. Space-time torsion could be the missing piece that connects general relativity with quantum mechanics and allows for a more unified description of the forces that govern the universe. The idea that space-time itself is subject to both curvature and torsion could help reconcile the seemingly disparate forces, potentially leading to a deeper understanding of the universe's fundamental structure. The exploration of space-time torsion also holds promise for the study of black holes. These mysterious objects, formed from the collapse of massive stars, are among the most extreme environments in the universe. Their gravitational pull is so strong that not even light can escape, and they present a natural laboratory for testing the limits of our understanding of gravity. General relativity predicts that the singularity at the center of a black hole is a point of infinite density, where the laws of physics as we know them break down. However, many physicists believe that a more complete theory of gravity, incorporating torsion and quantum mechanics, could provide a way to understand the behavior of black holes more fully, particularly at their core. Incorporating torsion into our understanding of black holes could help resolve some of the paradoxes surrounding these enigmatic objects. For instance, the information paradox has been one of the most puzzling questions in black hole physics. According to general relativity, information that falls into a black hole is lost forever, which contradicts the principles of quantum mechanics, which state that information must be preserved. If torsion plays a role in shaping the spacetime around black holes, it could offer a way to resolve this paradox, possibly providing a mechanism through which information could be preserved or even escape from a black hole. Moreover, torsion could shed light on the behavior of spacetime in the vicinity of other exotic objects, such as neutron stars, wormholes, and cosmic strings. Neutron stars, like black holes, are incredibly dense objects that warp spacetime in profound ways. By incorporating torsion into our understanding of these objects, we might be able to gain new insights into their structure and behavior, as well as the forces that govern them. The search for dark matter and dark energy has been one of the most exciting areas of research in recent years. Despite their apparent dominance in the universe, both dark matter and dark energy remain largely invisible, detectable only through their gravitational effects. Dark matter is believed to make up about 27% of the universe's total mass energy content, yet it has never been directly observed. Dark energy, on the other hand, is thought to account for about 68% of the universe's energy density, and is responsible for the observed acceleration of the universe's expansion. If spacetime torsion can provide a more complete understanding of gravity, it could offer a new way of thinking about these elusive phenomena. Rather than invoking the existence of unknown particles or energy fields, torsion might explain the observed effects of dark matter and dark energy as a natural consequence of the geometry of spacetime. For instance, if torsion alters the behavior of gravity on large scales, it could mimic the effects of dark matter, explaining the observed rotation curves of galaxies without the need for additional, unseen mass. Similarly, the accelerated expansion of the universe could be understood as the result of torsion's influence on spacetime itself, rather than the action of a mysterious energy field. By framing dark matter and dark energy as manifestations of spacetime torsion, we could make significant strides toward understanding these enigmatic components of the universe. As we continue to explore the role of spacetime torsion in alternative gravity theories, it's important to keep in mind that the scientific community is still far from reaching a consensus on the ultimate nature of gravity, dark matter, and dark energy. While the ideas presented here are intriguing, they remain speculative, and much more research is needed before we can fully embrace torsion as a viable explanation for these cosmic mysteries. However, the potential implications of this theory are too profound to ignore, and the exploration of torsion-based models is likely to be a key focus of future research in both theoretical physics and cosmology. Whether or not torsion turns out to be the key to unlocking the mysteries of dark matter and dark energy, the very fact that we are contemplating such radical ideas is a testament to the power of human curiosity and the relentless pursuit of knowledge. The universe, with all its complexity and wonder, continues to surprise us at every turn, and spacetime torsion is just one example of how the quest for understanding can lead us down unexpected and fascinating paths. As we continue to explore spacetime torsion, it's important to consider the impact such a theory could have on the broader scientific landscape. If torsion proves to be a valid modification of general relativity, it would not only revolutionize our understanding of gravity, but also spark a complete reevaluation of established models of the universe. The implications extend far beyond dark matter and dark energy. This could open the door to new ways of thinking about fundamental forces, matter, and the very fabric of spacetime itself. First, consider how torsion could affect our understanding of quantum field theory, QFT. QFT is one of the cornerstones of modern physics, describing how particles interact through fields. While successful in many areas, QFT has struggled to reconcile itself with general relativity. The introduction of torsion could provide a bridge between the quantum world and the cosmic scales governed by gravity. For instance, if torsion modifies the curvature of spacetime in a way that's not captured by general relativity, it might lead to new interactions between quantum fields that are currently unknown. This could drastically reshape our understanding of particle physics and the forces that govern matter at the smallest scales. Moreover, the inclusion of torsion could prompt a reconsideration of existing cosmological models. For decades, the lambda cold dark matter, lambda CDM, model has been the standard framework for explaining the evolution and large-scale structure of the universe. This model relies on the assumption that dark matter and dark energy are real entities, whose gravitational effects shape the universe. But what if these phenomena are not independent, but rather, a manifestation of a deeper, more fundamental property of spacetime itself? Spacetime torsion could provide a new, more elegant explanation for the observed effects attributed to dark matter and dark energy, possibly eliminating the need for exotic, undetectable particles or energy fields. In the context of cosmology, one of the key questions that spacetime torsion might help to address is the early universe's behavior, especially during the period known as cosmic inflation. Cosmic inflation is the theory that the universe underwent a rapid, exponential expansion in the first few moments after the Big Bang. This process is thought to have smoothed out irregularities in the distribution of matter, creating the nearly homogeneous universe we observe today. However, the exact mechanism behind inflation is still unclear, and many models invoke hypothetical scalar fields or other forms of energy to explain it. Torsion could offer an alternative explanation for inflation, where the geometry of spacetime itself undergoes a rapid, torsional twist, driving the expansion of the universe without requiring any additional fields or forces. The ramifications of such a theory are far-reaching. If torsion can explain cosmic inflation, it would provide a more unified theory of the early universe, potentially reducing the number of assumptions and parameters required to describe its evolution. This would be a major step toward the long-sought goal of a theory of everything, a single framework that explains both the large-scale structure of the cosmos and the behavior of particles at the quantum level. At the same time, exploring spacetime torsion offers a new way to think about the origins of the universe itself. In conventional models, the Big Bang is often described as the moment when spacetime itself began, with a singularity from which everything emerged. But if torsion plays a role in shaping spacetime, the birth of the universe might not have been as simple as a singular point of creation. Instead, it could involve a more intricate, dynamic process, where spacetime itself undergoes torsional transformations, leading to the creation of the universe as we know it. This opens up the possibility of multiple Big Bangs, or cycles of creation and destruction, challenging the notion of a single, unique beginning to the universe. The study of space-time torsion could also have important implications for the search for extraterrestrial life. As we've seen, the universe is full of strange and mysterious phenomena, and our understanding of the fundamental forces that shape it is far from complete. By considering the effects of torsion on space-time, we might be able to develop new ways of detecting and understanding the phenomena that could be indicative of life elsewhere in the cosmos. For example, the torsional properties of spacetime could have unique signatures that could potentially be detected by future space missions or observatories, offering new ways of identifying habitable environments, or even extraterrestrial civilizations. This would also impact our approach to the search for extraterrestrial intelligence, SETI. Most SETI efforts focus on detecting electromagnetic signals from distant civilizations. However, if torsion has a profound effect on spacetime itself, it could alter the way in which information is transmitted across the cosmos. Just as gravity waves were only recently detected after being predicted by Einstein's theory of general relativity, the effects of torsion might be similarly detectable in the future. It's possible that advanced civilizations could use these properties to communicate, manipulate spacetime, or even travel vast distances in ways that we are currently unable to comprehend. Moreover, the exploration of space-time torsion could provide a new perspective on some of the most puzzling phenomena in astrophysics. For example, the idea that torsion could influence the behavior of neutron stars, black holes, and other exotic objects provides a new avenue for investigating their internal structure and dynamics. Neutron stars, which are remnants of massive stars that have collapsed under their own gravity, are particularly interesting in this context because they represent some of the densest objects in the universe. Their extremely strong gravitational fields warp spacetime in ways that are not fully understood, and the introduction of torsion could provide new insights into the forces at play within these objects. Similarly, black holes, which continue to be a source of fascination and mystery for scientists, could reveal even more secrets if we consider the role of torsion in their formation and behavior. While general relativity predicts that the center of a black hole, the singularity, is a point of infinite density and curvature, torsion-based theories suggest that the true nature of a black hole's interior may be far more complex. Instead of a singularity, there could be a more complicated structure, influenced by the twisting and curving of spacetime itself. This could fundamentally alter our understanding of what happens when matter falls into a black hole, as well as how information is handled by these enigmatic objects. The incorporation of torsion into our understanding of gravity also prompts new questions about the nature of time itself. In general relativity, time is treated as part of the four-dimensional fabric of spacetime, influenced by the presence of mass and energy. But torsion could imply that time is not as uniform and unidirectional as we have come to believe. Instead, it might be influenced by more subtle properties of spacetime, leading to the possibility of alternative flows of time, perhaps even opening the door to time travel or alternative realities. The implications of this are staggering, not only for our understanding of the cosmos, but for our very concept of reality itself. The exploration of space-time torsion could lead to practical applications that we can hardly imagine today. Just as general relativity led to the development of GPS technology and other practical technologies based on our understanding of spacetime, the discovery of new torsional properties could have unforeseen consequences for technology. It's possible that future breakthroughs in physics could lead to new forms of energy generation, more efficient space travel, or even the ability to manipulate spacetime on a practical level. The study of torsion could open up entirely new fields of science and engineering, leading to a new era of discovery that touches every aspect of human life. As the scientific community continues to explore the mysteries of spacetime, torsion remains a fascinating and potentially transformative concept. While much work remains to be done, the possibility that torsion could provide answers to some of the biggest questions in physics, questions about gravity, dark matter, dark energy, and the fundamental nature of the universe, is both exhilarating and humbling. It's a reminder that the universe is far more complex and mysterious than we can currently understand, and that the pursuit of knowledge is an ongoing journey, full of surprises and new horizons. As we delve further into the idea of space-time torsion and its potential impact on our understanding of the universe, it's important to examine the broader consequences of a theory that challenges the very foundations of modern physics. Space-time torsion, if validated, would not just offer solutions to existing problems but could redefine how we approach scientific inquiry itself. This shift in perspective may require a rethinking of how we observe the cosmos, design experiments, and interpret data, fundamentally altering the trajectory of astrophysics, cosmology, and even quantum mechanics. One of the most profound impacts of integrating torsion into our understanding of spacetime is how it could alter the interpretation of the cosmos on both large and small scales. The very geometry of spacetime, the fabric upon which everything in the universe is written, would be fundamentally different from what we currently understand. The classic model, based on general relativity, treats spacetime as a smooth, curved fabric influenced by mass and energy. But if torsion is indeed a fundamental feature of spacetime, then this fabric could be more complex, exhibiting a twisting and shearing motion that could affect how gravitational waves propagate, how objects interact with one another, and how we interpret cosmic events. On the large scale, torsion could alter the structure of the universe itself. For instance, one of the long-standing mysteries in cosmology is the way galaxies form and evolve. We've already observed that galaxies are surrounded by vast halos of dark matter, and their rotation curves suggest that there's more mass in these systems than can be accounted for by visible matter. The leading explanation for this discrepancy has been the presence of dark matter, an invisible substance that interacts with gravity but not with light. But torsion theories could present an entirely different solution. Instead of dark matter being a substance that exists separately from the ordinary matter we see in the universe, torsion could offer a more elegant explanation. The gravitational effects attributed to dark matter might, in fact, be the result of the twisting of spacetime at the galactic scale. In this view, the mass that is missing from galaxies and clusters may not be missing at all. It could be an effect of torsion in the fabric of spacetime that alters the behavior of matter at large scales, bending our perceptions of mass and gravity. This could lead to a complete overhaul of the way we think about galaxy formation, structure, and dynamics. On the small scale, torsion could provide new insights into the behavior of fundamental particles. Quantum mechanics, the theory that governs the smallest scales of nature, has long struggled to reconcile with the smooth, curved spacetime described by general relativity. However, if torsion modifies the structure of spacetime at the quantum level, it could allow for a better understanding of quantum gravity, a theory that has eluded physicists for decades. In essence, torsion could serve as a bridge between the quantum world and the relativistic world, offering a path to unifying the fundamental forces of nature. The role of torsion could also significantly impact our approach to gravity waves, one of the most exciting recent discoveries in astrophysics. When two massive objects, like black holes or neutron stars, collide and merge, they send ripples through the fabric of spacetime. These ripples, known as gravitational waves, were first detected in 2015, confirming one of the most profound predictions of general relativity. But what if torsion modifies how these waves propagate? Could it alter their strength, frequency, or shape? By incorporating torsion into our models of gravitational waves, we could gain new insights into the behavior of the universe's most extreme objects and events. This would not only deepen our understanding of gravity but could also provide us with an entirely new way of observing the universe, through the study of torsional waves and their effects on matter and energy. Additionally, the concept of torsion might offer clues into some of the most enigmatic phenomena in modern physics, including the behavior of black holes. Black holes, with their immense gravitational pull, are notorious for bending the fabric of spacetime to such an extreme that nothing, no light, no information, can escape their grasp. The introduction of torsion could fundamentally alter our understanding of black hole interiors. In classical general relativity, the singularity at the center of a black hole is a point of infinite density, where the known laws of physics break down. However, if torsion is present in spacetime, it may prevent the formation of such a singularity, replacing it with a more complex structure. This could open up entirely new avenues of research into what happens at the core of a black hole, and whether information can escape its gravitational pull in ways that we've yet to understand. Moreover, torsion could help shed light on the role of dark energy, another of the greatest mysteries in modern cosmology. Dark energy is thought to be responsible for the accelerated expansion of the universe, but its exact nature remains elusive. It's often treated as a hypothetical form of energy that permeates space, exerting a repulsive force that counteracts gravity on cosmological scales. But could torsion be responsible for this observed acceleration? If torsion alters the geometry of spacetime, it might affect the way in which the expansion of the universe behaves, mimicking the effects of dark energy without requiring the existence of an unknown substance. This would offer a more straightforward and potentially more elegant explanation for the accelerating expansion, further strengthening the idea that spacetime itself may be far more dynamic and complex than we have traditionally understood. Furthermore, the inclusion of torsion in our models of gravity may lead to new insights into the behavior of the universe at its earliest stages. The Big Bang, traditionally viewed as the beginning of both space and time, remains one of the most puzzling events in cosmology. Current models suggest that the universe originated from a singularity, an infinitely dense point where the laws of physics break down. However, if torsion modifies the structure of spacetime at both large and small scales, it may provide a new mechanism for the early expansion of the universe, potentially altering our understanding of the Big Bang and the subsequent cosmic inflation. Instead of a singular, dramatic event, the birth of the universe could have been more gradual, influenced by the twisting and turning of space-time itself. This new perspective could open up entirely new theories of cosmic evolution, possibly offering a clearer understanding of how the universe transitioned from a dense, hot state to the vast, complex cosmos we observe today. The implications of space-time torsion extend beyond the realm of theoretical physics and into the practical applications of technology. As mentioned earlier, the effects of torsion on space-time might eventually lead to new ways of manipulating gravitational forces. If we can better understand how torsion affects matter and energy, we may be able to develop new technologies that take advantage of these properties. For example, torsion could potentially be used to enhance propulsion systems, allowing for faster and more efficient travel through space. It might also lead to breakthroughs in energy generation, where torsional effects could be harnessed to create new forms of energy or improve the efficiency of existing technologies. In terms of space exploration, the study of space-time torsion could eventually open up new frontiers for human travel. The ability to manipulate space-time at the fundamental level could lead to the development of advanced propulsion systems that could drastically reduce travel times between stars. Imagine traveling to distant exoplanets, or even other star systems in a fraction of the time it currently takes with traditional propulsion methods. While this may sound like science fiction, it's precisely the kind of groundbreaking technological advancement that could arise from a deeper understanding of space-time itself. Ultimately, the exploration of space-time torsion represents one of the most promising frontiers in modern physics. The idea that the very fabric of the universe may be twisted and shaped in ways we've only begun to understand holds immense potential. From redefining our understanding of gravity and dark matter to offering new solutions to the fundamental mysteries of the universe, torsion could be the key that unlocks some of the most profound questions in science. As researchers continue to explore this fascinating concept, we may find ourselves on the brink of a new era of discovery, one that could change the way we view the universe, our place within it, and the nature of reality itself. The exploration of space-time torsion is a thrilling venture, for it may eventually bridge the gap between the macrocosm of the universe and the microcosm of quantum mechanics, two realms that have resisted full unification for decades. As we explore deeper into these possibilities, the broader implications of torsion reach far beyond theoretical physics and into the heart of our understanding of the cosmos. To truly grasp the profound impact space-time torsion may have, we need to reflect on how it integrates into existing models and what it can tell us about the universe at its most fundamental level. One of the most intriguing aspects of introducing torsion into the framework of general relativity is the possibility it holds for understanding the elusive concept of quantum gravity. For decades, physicists have been struggling to reconcile general relativity, which governs the large-scale structure of the universe, with quantum mechanics, which governs the microscopic realm of subatomic particles. These two pillars of modern physics operate under vastly different rules. General relativity is deterministic, while quantum mechanics is probabilistic. This dichotomy has led to numerous unsuccessful attempts at developing a theory of quantum gravity, a unified framework that could explain both realms. Torsion could provide a vital piece of the puzzle. In traditional general relativity, space-time is modeled as a smooth, curved manifold that is shaped by the distribution of mass and energy. However, when torsion is introduced, space-time is no longer just curved but also twisted. This modification may open up new avenues for describing quantum gravity, potentially offering a mechanism by which quantum effects influence the curvature and twisting of space-time. In this framework, quantum particles could exhibit behaviors that are influenced not only by gravity but by the torsion of space-time itself, potentially leading to new insights into how gravity operates at the quantum level. One of the key challenges in developing a theory of quantum gravity is the question of how to incorporate the effects of space-time on a subatomic scale. If torsion is indeed a fundamental feature of space-time, its effects could be observable at scales far smaller than those currently accessible by experiment. As we push the boundaries of our detection capabilities, we might find that space-time torsion becomes increasingly significant in the behavior of quantum systems. This could provide the much-needed experimental foundation for unifying general relativity with quantum mechanics, a breakthrough that would reshape the entire field of theoretical physics. Beyond quantum gravity, space-time torsion may also have profound implications for our understanding of the fundamental forces of nature. At present, we recognize four fundamental forces: gravity, electromagnetism, the strong nuclear force, and the weak nuclear force. These forces are traditionally modeled using different theoretical frameworks. Gravity is described by general relativity, while electromagnetism and the nuclear forces are described by quantum field theory. Despite their apparent differences, there is a growing belief that all four forces may be manifestations of a single, underlying force, one that has been unified in the early universe but has since separated into distinct forms. Space-time torsion could provide the missing link in this grand unification. If torsion is a fundamental property of space-time, it may interact with the other forces in unexpected ways, potentially revealing connections that are not immediately obvious within our current understanding. In particular, torsion might help us understand the origin of the fundamental forces in the early universe, perhaps offering insights into why gravity behaves so differently from the other forces. It's possible that torsion could play a key role in explaining why gravity is so weak compared to electromagnetism or the nuclear forces, an anomaly that has puzzled scientists for centuries. But the influence of space-time torsion is not confined to the abstract world of theoretical physics. If its effects can be detected and understood, they could have far-reaching practical applications, some of which might seem straight out of science fiction. The manipulation of space-time itself, whether through the twisting of its structure or the creation of artificial gravitational fields, could have revolutionary implications for technology. Propulsion systems, energy generation, and even communication could all benefit from advances in understanding torsion. In particular, space-time manipulation could open the door to entirely new forms of propulsion. Traditional rocket engines operate by expelling mass at high velocities, generating thrust through Newton's third law. However, if we can manipulate space-time itself, perhaps by creating localized torsion fields, we could theoretically bypass the need for propellant altogether. This type of propulsion system would be vastly more efficient than anything we currently have, and it could enable faster-than-light travel. While this remains firmly in the realm of speculation, the study of space-time torsion is beginning to reveal the fundamental properties of space-time that might one day make such technologies possible. Similarly, the understanding of torsion could lead to breakthroughs in energy generation. Torsional effects in space-time may allow for the extraction of energy from the vacuum of space itself, a concept known as zero-point energy. While this idea has long been the subject of speculation, the deeper exploration of space-time torsion could provide the theoretical underpinnings necessary to realize it. If we could harness the energy associated with torsion fields, we might be able to develop new forms of clean, virtually limitless energy, capable of powering entire cities or even interstellar spacecraft. Furthermore, the implications of space-time torsion extend beyond the material universe and into the realm of information. One of the most profound questions in modern physics is how information behaves in the universe, particularly in extreme environments like black holes. According to the holographic principle, all the information contained within a region of space is encoded on the boundary of that region. This has led to fascinating discussions about the nature of reality itself, whether the universe is fundamentally a projection of information encoded on a two-dimensional surface. If torsion is a fundamental aspect of space-time, it could have implications for how information is processed, stored, and transmitted throughout the cosmos. In particular, space-time torsion may offer insights into the black hole information paradox. In general relativity, it was believed that information that falls into a black hole is lost forever. However, this is at odds with the principles of quantum mechanics, which state that information cannot be destroyed. If torsion plays a role in the structure of space-time, it may provide a mechanism by which information is not lost but is instead encoded in the twisting structure of the black hole itself. This would resolve one of the most puzzling questions in modern physics, and could lead to a deeper understanding of the fundamental nature of information in the universe. The study of space-time torsion is not just about filling in gaps in our understanding of gravity and the universe. It is a radical rethinking of the very fabric of reality. As we continue to explore this concept, we may find that space-time torsion is not just a theoretical curiosity, but a key to unlocking some of the greatest mysteries of the cosmos. From explaining dark matter and dark energy to revealing new insights into quantum gravity, black holes, and the origin of the universe, torsion could be the gateway to a deeper, more complete understanding of the universe. And while the full implications of this research are still unfolding, one thing is clear: the future of physics lies in the twisting, turning, and reshaping of spacetime itself. As we continue to delve into the profound implications of spacetime torsion, we must shift our focus to the observable universe and how these theoretical concepts could be brought to life in experiments. The complexity and beauty of spacetime torsion might seem abstract, but its potential for advancing our understanding of the universe extends to the frontiers of observational astrophysics. One of the most pressing questions we face is whether torsion has any measurable impact on the fabric of spacetime, particularly on cosmic scales where phenomena like dark matter and dark energy operate. Dark matter and dark energy, two of the most mysterious and enigmatic components of the universe, have thus far eluded direct detection. Dark matter, believed to make up about 27% of the universe's mass energy content, has never been observed directly. Instead, its existence is inferred from its gravitational effects on visible matter, such as galaxies and galaxy clusters. Dark energy, on the other hand, is an even more perplexing entity, responsible for the accelerated expansion of the universe. It accounts for roughly 68% of the universe's energy content, yet its nature remains completely unknown. The introduction of spacetime torsion as a possible modification to general relativity presents a tantalizing possibility that torsion could account for these mysterious phenomena. Traditionally, scientists have tried to explain the effects attributed to dark matter and dark energy through extensions of general relativity, or by proposing new, exotic forms of matter and energy. However, the standard model of cosmology, the lambda-CDM model, still cannot fully explain some of the observed anomalies in cosmic behavior. This is where spacetime torsion may play a pivotal role in unlocking the mysteries of the universe. To understand how torsion could potentially explain dark matter and dark energy, we need to consider the effects of torsion on the curvature of spacetime. In the conventional model, gravity is described as the curvature of spacetime caused by the presence of mass and energy. However, torsion introduces an additional twist to this framework. Instead of spacetime merely bending in response to mass, it could also twist, altering the way objects move through it. This twisting could create additional gravitational effects, ones that mimic the effects attributed to dark matter. If torsion were present in spacetime, it could exert influence on the distribution of mass in a way that leads to the gravitational effects we observe but cannot explain with ordinary matter alone. For instance, galaxies rotate at speeds that cannot be accounted for by the visible mass within them, suggesting that there is some unseen mass exerting additional gravitational pull. Dark matter is the proposed solution to this puzzle, but torsion could provide an alternative explanation by modifying the gravitational dynamics in such a way that the effects of dark matter are no longer necessary. The twisted structure of spacetime itself could be responsible for the anomalous rotation speeds of galaxies, and in this case, no new form of matter would need to be invoked. Similarly, dark energy, which drives the accelerated expansion of the universe, might be explained by torsion as well. In the context of general relativity, dark energy is modeled as a cosmological constant, a constant energy density that fills space homogeneously. But torsion, with its ability to twist and shape the structure of spacetime, could potentially explain the observed acceleration without invoking a mysterious energy field. By altering the way spacetime behaves on cosmic scales, torsion could cause the universe to expand at an accelerating rate. In this way, spacetime torsion could act as an effective dark energy, providing the push necessary to explain the observed expansion without resorting to the introduction of an unknown form of energy. But how can we test these ideas? The most direct way to investigate the presence of space-time torsion would be through the observation of gravitational effects that cannot be explained by general relativity alone. In recent years, advances in observational astronomy and cosmology have provided increasingly precise measurements of cosmic phenomena, such as the rotation curves of galaxies, the motion of galaxy clusters, and the expansion of the universe. These observations could be sensitive to the twisting effects of torsion, allowing researchers to detect deviations from the predictions of general relativity. For example, gravitational waves, ripples in spacetime caused by the acceleration of massive objects, are a prime candidate for detecting the effects of torsion. These waves have already been detected by observatories like LIGO and Virgo, confirming one of the key predictions of general relativity. However, if torsion affects spacetime in a way that alters the propagation of gravitational waves, we could see subtle differences in the way these waves behave. For instance, if torsion is present, gravitational waves might travel slightly differently through twisted regions of spacetime, potentially leading to observable effects on their amplitude or velocity. By analyzing the properties of gravitational waves, we could potentially detect the signature of spacetime torsion. Another avenue of exploration involves the cosmic microwave background, CMB, the afterglow of the Big Bang. The CMB provides a snapshot of the universe when it was only about 380,000 years old, and is a crucial tool for understanding the large-scale structure and evolution of the universe. If torsion affects the curvature of spacetime, it could leave an imprint on the CMB, altering the way light travels through the early universe. By analyzing the subtle fluctuations in the CMB, scientists could look for patterns that suggest the presence of torsion. These imprints might manifest as distortions in the temperature or polarization of the CMB, which could provide evidence for space-time torsion at the time of the universe's formation. Additionally, the study of galaxy clusters could reveal the presence of torsion. Galaxy clusters, the largest gravitationally bound structures in the universe, provide an ideal testing ground for alternative gravity theories. The gravitational dynamics of galaxy clusters, including the motion of galaxies within clusters and the distribution of hot gas between them, are sensitive to the curvature and structure of spacetime. If torsion modifies the way gravity operates on large scales, we could see differences in the way galaxies and gas behave within clusters. By studying these behaviors, we could potentially detect the signature of torsion and, in turn, gain insight into the nature of dark matter and dark energy. The detection of spacetime torsion would not only revolutionize our understanding of gravity, but also open up new possibilities for technologies that manipulate spacetime. If we can understand and harness the twisting of spacetime, we may be able to develop new methods of propulsion, communication, and energy generation that were once thought to be purely speculative. Technologies like warp drives, which rely on the manipulation of spacetime for faster-than-light travel, could become a reality, transforming space exploration and even the possibility of interstellar travel. However, even with these exciting possibilities, the study of spacetime torsion is still in its infancy, and much work remains to be done. Theoretical models must be refined, and experimental techniques must be developed to detect and measure the effects of torsion. As we continue to push the boundaries of our understanding of the universe, spacetime torsion may prove to be the key to unlocking some of the most profound mysteries of the cosmos. By investigating the twisting, turning fabric of spacetime, we may uncover the secrets of dark matter, dark energy, and quantum gravity, secrets that could reshape our understanding of the universe itself. The potential implications of spacetime torsion are not just confined to the realm of astrophysics and cosmology. By offering a new perspective on the fundamental workings of the universe, spacetime torsion could also shed light on some of the most profound questions in theoretical physics. For example, the relationship between general relativity and quantum mechanics is one of the greatest unsolved problems in modern physics. General relativity describes the large-scale structure of the universe, while quantum mechanics governs the behavior of particles on the smallest scales. These two frameworks, despite their immense success in their respective domains, have never been fully reconciled. Spacetime torsion, as a modification of general relativity, could provide the bridge needed to unify these two theories. In fact, some approaches to quantum gravity already incorporate torsion as a fundamental aspect of spacetime. One such theory is loop quantum gravity, which attempts to describe gravity in terms of quantum mechanics. In loop quantum gravity, spacetime is thought to be quantized, composed of discrete units of space and time. These units are interconnected by loops, and the introduction of torsion could provide a mechanism by which the quantum properties of spacetime are manifested in observable gravitational effects. The incorporation of torsion into quantum gravity could offer insights into the nature of singularities, such as those found at the center of black holes. Singularities, as predicted by general relativity, are points where spacetime becomes infinitely curved, and current physical theories break down. The presence of torsion could smooth out these singularities, providing a way to describe them in a mathematically consistent manner. Instead of the infinite curvatures predicted by traditional general relativity, torsion might introduce a finite, well-defined structure at the heart of black holes, potentially leading to a better understanding of the nature of these enigmatic objects. Furthermore, the study of torsion could have far-reaching implications for the foundations of quantum mechanics itself. In the quest to unify the fundamental forces of nature, researchers have long sought to discover a theory of everything, a single framework that explains all the forces in the universe, from gravity to electromagnetism to the strong and weak nuclear forces. Spacetime torsion, if proven to be a real physical phenomenon, could play a role in this unification, offering a new avenue for exploring how the forces interact at the most fundamental level. By examining how torsion influences both the macroscopic and microscopic behavior of the universe, scientists could uncover new insights into the fundamental laws that govern everything from the behavior of galaxies to the interactions between subatomic particles. As we continue to probe the mysteries of spacetime, the study of torsion may also provide answers to some of the most puzzling questions about the nature of time itself. Time, as we understand it, is intricately connected to space in the framework of general relativity, forming the concept of spacetime. However, the flow of time is still not fully understood. In some interpretations of quantum mechanics, time is viewed as an emergent property, something that arises from deeper, more fundamental processes. Spacetime torsion, with its twisting and warping effects, might offer a new perspective on how time behaves at a quantum level, potentially revealing the true nature of time's passage. The implications of spacetime torsion also extend to the study of other exotic phenomena in the universe. For instance, the study of neutron stars, ultra-dense remnants of massive stars that have exploded in supernovae, could provide valuable clues about the presence of torsion. Neutron stars have extreme gravitational fields that bend and twist spacetime to an extent that makes them natural laboratories for testing modifications to general relativity. If torsion is present, it could affect the behavior of matter within these stars, providing observable differences in their gravitational interactions. By carefully studying the properties of neutron stars, such as their mass, radius, and the behavior of light as it passes near them, researchers could test the predictions of torsion-based models. Another fascinating avenue of exploration involves the study of gravitational lensing, the bending of light as it passes through massive objects like galaxies and black holes. In the conventional understanding of gravity, light follows the curvature of spacetime as predicted by general relativity. However, if spacetime torsion is present, it could cause additional distortions in the path of light. These distortions could provide a subtle but measurable signature of torsion, offering another way to test the validity of this hypothesis. By observing gravitational lensing events in detail, scientists may be able to detect the effects of torsion on the behavior of light, potentially confirming its existence and providing further evidence for alternative gravity theories. The idea of spacetime torsion also challenges some of our most deeply held assumptions about the structure of the universe. For centuries, physicists have worked under the assumption that spacetime is a smooth, continuous entity, governed by the rules of general relativity. However, the introduction of torsion suggests that spacetime may not be as smooth as we once thought. Instead, it could be a more complex, dynamic structure, influenced by the presence of mass, energy, and other fundamental forces. This could lead to a rethinking of many of the assumptions we've made about the nature of reality itself. Space-time torsion could provide a new lens through which we view the universe, one that reveals hidden dimensions and structures that were previously invisible to us. In addition to its theoretical implications, the exploration of space-time torsion could also lead to practical advances in technology. For example, the ability to manipulate space-time could have profound applications in areas such as transportation, energy generation, and communication. The idea of manipulating space-time for faster-than-light travel has long been a staple of science fiction, but if torsion can be harnessed, it might become a reality. Warp drives, which involve bending space-time to create a bubble that allows for faster-than-light travel, could be made possible through the manipulation of torsion. If we can understand how torsion works and how to control it, we may unlock the ability to travel across vast distances of space in a fraction of the time it currently takes. Similarly, the study of space-time torsion could lead to new breakthroughs in energy generation. If torsion affects the behavior of space-time in ways that alter the flow of energy, it might open up new methods of harnessing energy from the fabric of space itself. This could lead to the development of highly efficient energy systems, potentially revolutionizing the way we power our civilization. Additionally, the ability to manipulate space-time could have applications in communication technologies, allowing for faster and more secure methods of transmitting information across vast distances. Despite all the potential breakthroughs, however, the study of space-time torsion is still in its early stages. Theoretical models continue to evolve, and experimental techniques are being developed to test the predictions of these models. The road ahead is long and filled with challenges, but the potential rewards are immense. If we can unlock the secrets of space-time torsion, we could be on the cusp of a new era in our understanding of the universe, one that redefines the very fabric of reality itself. The mysteries of space-time are vast and profound, and space-time torsion offers a new and exciting path toward unraveling them. Whether it leads to a deeper understanding of dark matter and dark energy, a unification of general relativity and quantum mechanics, or groundbreaking new technologies, the study of torsion holds the key to some of the most fundamental questions in physics. As we continue to explore the twisting, bending, and warping nature of space-time, we may discover that the universe is far stranger and more complex than we ever imagined. The potential for discovery is limitless, and the journey into the heart of space-time is only just beginning. As we continue to explore the vast unknowns of space-time, the potential for unraveling new theories grows with every step. The concept of space-time torsion offers a tantalizing glimpse into a realm of physics that may provide not only answers to some of the most perplexing mysteries in the universe, but also radically alter how we perceive the fundamental structure of reality. While we've delved into the potential implications for dark matter, dark energy, and quantum gravity, it's important to step back and explore just how profound these changes might be, not only for the field of cosmology but for the way humanity interacts with the cosmos. One of the most crucial aspects to consider when investigating space-time torsion in alternative gravity theories is how it could fundamentally alter our understanding of gravity itself. In the standard model of physics, gravity is understood as the warping of space-time caused by mass and energy, a description outlined by Einstein's theory of general relativity. Gravity, as traditionally conceived, acts on all forms of mass and energy in the same manner, pulling objects toward one another in a manner consistent with the curvature of space-time. But this explanation only scratches the surface. What if gravity is not the sole player when it comes to how objects interact with one another in space? This is where the concept of space-time torsion comes in. By adding a twist to the very fabric of space-time, torsion introduces the possibility that gravitational effects could be accompanied by other, more subtle forces that influence the motion of celestial objects. In this context, torsion isn't just a theoretical curiosity, it becomes a potential driver of the universe's behavior. In fact, some physicists propose that torsion could influence the very way in which objects move through space-time, altering their trajectories in ways that could be measured, analyzed, and potentially harnessed. One compelling example of this can be found in the investigation of cosmic inflation, the period of rapid expansion of the universe that occurred just after the Big Bang. The standard model of cosmology suggests that inflation was caused by an extremely high-energy field that rapidly stretched space-time. However, some alternative theories posit that space-time torsion could have played a role in this early period of expansion. If torsion had been present during inflation, it could have provided an additional mechanism for the rapid stretching of space-time, perhaps even contributing to the formation of structures like galaxies and clusters of galaxies. Moreover, space-time torsion could provide a deeper understanding of the cosmological constant, a concept introduced by Einstein himself as a way to account for the observed acceleration of the universe's expansion. In the Standard Model, this constant is often associated with dark energy, a mysterious form of energy thought to be responsible for the accelerated expansion of the universe. However, the cosmological constant and its relationship to dark energy have remained elusive. Could torsion play a role in this acceleration? By modifying the equations that govern the universe's expansion, torsion could offer a new perspective on dark energy, providing a possible explanation for why the universe is expanding at an ever-increasing rate. In this sense, space-time torsion holds the potential to bridge the gap between some of the most challenging questions in modern physics. How do we explain the accelerating expansion of the universe? What is dark matter, and how does it influence the cosmos on both large and small scales? How do we reconcile quantum mechanics with general relativity? The answer to all these questions could lie in the twisting, turning geometry of spacetime itself. If torsion is indeed a real phenomenon, it could have profound implications for our understanding of the universe's structure and behavior, potentially offering a unified framework in which these disparate ideas come together. While the theoretical ramifications of space-time torsion are profound, the experimental challenges involved in testing its predictions are equally significant. Directly detecting the effects of torsion on spacetime is no simple task. Torsion, by its nature, is expected to produce extremely subtle effects on the fabric of spacetime. This means that any experiment designed to test the existence of torsion must be incredibly precise, capable of measuring minute variations in the curvature or behavior of spacetime. The sensitivity required to detect these effects puts a significant strain on current experimental techniques. Yet, scientists are making strides in developing methods to test the predictions of torsion-based theories. One promising avenue involves the study of gravitational waves. Gravitational waves, first detected in 2015, are ripples in the fabric of spacetime caused by the acceleration of massive objects, such as the collision of two black holes. These waves provide a unique opportunity to probe the structure of spacetime on the most fundamental level. If torsion is present, it could introduce subtle alterations in the way that gravitational waves propagate through space, providing a potential signal that could be detected by observatories like LIGO and Virgo. Another experimental approach involves the observation of the cosmic microwave background (CMB), the faint radiation left over from the Big Bang. The CMB contains a wealth of information about the early universe, and any effects caused by spacetime torsion during inflation would have left their imprint on this radiation. By studying the tiny fluctuations in the CMB, scientists hope to uncover clues about the presence of torsion in the early universe, potentially providing direct evidence for its role in cosmic evolution. The search for torsion may not stop at large-scale observations like gravitational waves or the CMB. Researchers are also investigating the potential effects of torsion on more familiar physical systems, such as the behavior of rotating bodies. In particular, the study of gyroscopes and other devices that measure rotational motion could provide insight into how torsion affects the spacetime fabric on a local level. These experiments are still in the early stages, but the results could provide crucial information about whether torsion is a real phenomenon or merely a theoretical curiosity. As we look ahead to the future, the quest to understand spacetime torsion is bound to play a central role in our pursuit of a unified theory of physics. If torsion is indeed a fundamental feature of spacetime, its discovery could revolutionize our understanding of the universe. In many ways, this search represents the next frontier in theoretical physics, a journey that could take us from the most microscopic scales of quantum mechanics to the vast reaches of the cosmos. The implications of such a discovery are almost beyond comprehension. A unified theory that incorporates spacetime torsion could rewrite the laws of physics as we know them, providing a framework in which the mysteries of dark matter, dark energy, quantum gravity, and the very nature of space and time can finally be understood. With each new discovery, we move closer to unraveling the fabric of the cosmos itself, and space-time torsion stands as one of the most intriguing and exciting possibilities on the horizon. Whether it's in the form of new theoretical insights, groundbreaking experimental results, or revolutionary technologies, the study of torsion will undoubtedly shape the future of physics for generations to come. The journey is far from over, and the universe, with all its mysteries and wonders, still has much to reveal. The journey to uncover the true nature of space-time torsion, and its potential implications for our understanding of the universe, continues to evolve in fascinating ways. As we press on, it becomes evident that the relationship between space-time torsion and the fundamental forces of nature, gravity, electromagnetism, and the strong and weak nuclear forces, is much more intricate than we may have imagined. This realization is leading scientists to reconsider how these forces interact, and more importantly, how they could be unified under a single, comprehensive theory. One area where space-time torsion's potential to reshape our understanding is particularly exciting is in the pursuit of quantum gravity. Quantum mechanics has long provided the most accurate descriptions of the microscopic world, explaining the behavior of particles and forces at incredibly small scales. However, when it comes to understanding how gravity works at these scales, quantum mechanics falls short. This is because, at the quantum level, space and time themselves become subject to the unpredictable fluctuations of quantum fields. These fluctuations present a fundamental challenge to general relativity, which treats spacetime as a smooth and continuous entity. Spacetime torsion offers a potential bridge between quantum mechanics and general relativity, two pillars of modern physics that have remained stubbornly incompatible. By introducing torsion as an intrinsic feature of spacetime, theorists believe that they may be able to describe gravity in a quantum framework. This could lead to the long-sought-after theory of quantum gravity, a unified theory that would describe the behavior of all four fundamental forces of nature in a single, coherent framework. One approach to achieving this goal is through the use of string theory, which posits that the fundamental particles of the universe are not point-like, but rather tiny, vibrating strings. String theory suggests that the properties of these strings are influenced not only by the known forces of nature but also by additional dimensions of space-time beyond the familiar three spatial dimensions and one time dimension. In this context, space-time torsion could play a crucial role in shaping the behavior of these extra dimensions, offering a pathway to a deeper understanding of the universe at the most fundamental level. As string theory continues to evolve, the role of torsion in these higher-dimensional spaces remains a subject of intense study. The presence of torsion may help to explain certain phenomena predicted by string theory, such as the behavior of black holes and the formation of singularities. Additionally, it could offer a new perspective on the so-called landscape problem in string theory, which involves the large number of possible solutions to the equations of string theory. By incorporating torsion into these models, scientists may be able to narrow down the range of possible solutions and gain a clearer understanding of the true nature of the universe. The potential applications of space-time torsion extend far beyond the realms of theoretical physics. If torsion is indeed a real phenomenon, its discovery could open the door to revolutionary new technologies that manipulate space-time in ways previously thought impossible. For example, space-time torsion may have applications in the realm of energy production. By tapping into the subtle effects of torsion on the fabric of space-time, it may be possible to create entirely new forms of energy generation that could provide clean, limitless power. This is, of course, speculative at this stage, but the very idea of harnessing the fundamental structure of spacetime itself for practical use is nothing short of extraordinary. Moreover, the study of torsion could have far-reaching implications for our understanding of the universe's fate. Many cosmologists believe that the universe is heading toward a big freeze scenario, in which the expansion of the universe continues to accelerate, eventually causing all stars to burn out and galaxies to drift apart. However, if torsion is involved in the dynamics of spacetime, it may offer an alternative explanation for the universe's accelerating expansion, suggesting that the ultimate fate of the cosmos could take a dramatically different turn. In particular, the interplay between torsion and dark energy may lead to a re-evaluation of the universe's long-term evolution. Instead of continuing to expand at an ever-increasing rate, the universe could experience a slowdown or even a reversal in its expansion. This could have profound implications for our understanding of the ultimate fate of all matter and energy in the cosmos. Could space-time torsion provide a mechanism for the universe to bounce back from the brink of collapse, leading to a cyclical model of cosmological evolution? Or could torsion allow for the emergence of entirely new forms of matter and energy that would reshape the course of cosmic history? Of course, these questions remain speculative, and much more research is needed to determine the true role of torsion in the universe's evolution. However, the possibilities are both exciting and humbling. The discovery of space-time torsion would mark a turning point in our understanding of the cosmos, offering a new lens through which to view the most profound mysteries of existence. As we continue to study the intricacies of space-time and gravity, the importance of space-time torsion in shaping our universe becomes ever more apparent. Whether it's through its potential to explain dark matter and dark energy, its connection to quantum gravity, or its potential applications in new technologies, torsion stands at the crossroads of some of the most exciting frontiers in physics. By incorporating this concept into our understanding of the universe, we may one day unlock the key to the deepest mysteries of space-time itself. For now, scientists are at the forefront of a revolution in our understanding of the universe. The study of space-time torsion is still in its infancy, but the progress made so far is already beginning to paint a picture of a universe far more complex and mysterious than we had previously imagined. In the coming years, new discoveries and advancements in both theoretical and experimental physics will no doubt continue to push the boundaries of what we know, and the role of space-time torsion in this process will only grow in importance. As our understanding of space-time deepens, it's clear that the universe holds secrets that are waiting to be uncovered. And while space-time torsion may be just one piece of the puzzle, it represents a promising avenue of exploration that could lead to a deeper, more unified understanding of the cosmos. The future of physics is bright, and the answers to the universe's most profound mysteries may be closer than we think. This video is for educational or entertainment purposes only, and information provided in the video may be incorrect. Like the video and subscribe to the channel for more such amazing videos.